Break time is over. When he'll come? आ रहा है. Waiting for you since morning. Where are you? आ रहा है. Answers in physics numericals. आ रहा है. JEE mains and NEET dates in COVID. आ रहा है. It's monsoon time. आ रहा है. So students, whether these things are going to happen or not, but yes, we are going to celebrate your trust on 28th of February 2022 as Vishwas Divas. So guys, stay tuned right to the channel as it will be the most historic moment and a grand surprise is going to come. Thank you. Center of mass. Angular momentum. Torque. So students, lecture of rotational motion is loading. Hello bachcho, Sat Sri Akal and Namaste from my side. So this was a teaser as usual, right, regarding the concepts that we are going to see in this session. See, this initiative was this initiative was as of late for you all, right, and even you showered a love for that, right. I can see I have read the comments in my previous videos also. Some students are saying that, sir, we have done this lecture, we have done this chapter, but still we came here to see the teaser. Thanks a lot, right, for that. But students, I want to tell you all, right, see, with teaser is just a glimpse of the entire session, how we are going to study, right, and with what visuals and with the what new different techniques, right. So it doesn't mean you should be here only for the teaser, right. Kindly be present into the lectures also, right. Okay, it is also the right most important part. Okay, so as usual, thanks a lot. Okay. So things apart. So this is Indrajeet Singh, your own physics educator, welcoming you all to the most sensible platform, right, of an ed tech, right, for the aspirants, those who are preparing for JEE and NEET kind of the competitive examinations. And as you all know, the PW is a box of surprises, right? We are growing high. So today's lecture is regarding the rotational motion. Now let's start, right? Now what topics we are going to cover in this, right? We are going to cover the center of mass, the moment of inertia, torque, some of the concepts related to the dynamics, angular momentum and conservation, right? And we are going to end up this session with the rolling, right? Some of the important shortcuts in the rolling we are going to discuss. So, right, in this case, you are really you are going to enjoy the each and every moment of this session. Okay, so now let's begin. As usual, it's our tradition, right, to discuss the flow chart, right? So a flow chart in another sense, see, rotation, right, it is having, see, entire rotational motion, see, till now, right, till now, if I'm talking about, say, this is a champion series, it was started with the lecture units and measurement, followed by 1D, 2D, NLM, work, energy and power, right, and now we have reached up to the rotational motion. So I want to tell you all, right, okay, let's see, it's a very simple stuff. In first chapter, we did the entire things of measurement. After that, we dealt with the motion, not with its cause. After that, we moved on to the motion in 2D. Still, we are not dealing with the cause. Slowly, we reached to the NLM, and yes, now we were dealing with the cause. right? Then we reached to the work energy and power with the cause of the motion force, right? We were dealing with the energy. Till now, we haven't considered the configurations of the particle. We were considering the all objects as a particle, right? But in this case, yes, we are going to deal in this session, in this chapter. You can understand the flow, how the syllabus is designed, right? You can understand the flow, how that syllabus is designed, right? It's a very simple stuff, right? In this section, in this chapter, yes, we are going to discuss we are going to deal with the cause of the motion also, but with the configuration of the body, yes, with the structure of the body, right? We are going to discuss with the structure of the body, right? So rotation, the first part of the rotation is completely, right, based on center of mass, right? In the center of mass topic, we are going to discuss, right, what actually the rigid body is, right? Second, we are going to discuss the center of mass for the rigid bodies and the respective formulas, right? Center of mass for the combined bodies, right? And even center of mass, moving center of mass, right? Combined bodies and cavities, right? Moving center of mass, this thing, right, we are going to discuss. This is all about the center of masses, right? After that, obviously, right, we are going to deal with the MOI, that stands for moment of inertia, right? MOI, that stands for moment of inertia, right? In this moment of inertia, we are going to discuss what actual MOI is, all formulas of the rigid bodies, right, of MOI. After that, we are going to see the perpendicular axis theorem, right? And then we are going to discuss the parallel axis theorem, right? And the respective formulas, and obviously moment of inertia for the combined bodies, right? And the bodies with the cavities, right? After that, the rotational motion is having the classification of dynamics. Yes, the rotational dynamics, right? Okay, in rotational dynamics, we are having lots of things, right? Okay, the first important part of the rotational dynamics is torque, right? And its equilibrium conditions, right? Basically, we are going to deal with the two kind of the equilibrium conditions. First, the conditions for the translational motions and the conditions for the rotational motion, right? After that, we are having the angular momentum, right? In this angular momentum, obviously, we are going to discuss, right? Okay, with the conservation of angular momentum, and actually, right, the example of what types of the angular momentum is variables, linear variables, angular variables, and everything we are going to discuss, right? And the last part of the rotational motion is nothing else but a rolling, right? The most important part into the rolling, right? Types of rolling, and the most confused, or like most important part in which the students get confused is about how to identify the direction of the friction into the rolling, right? So direction of friction in rolling, this stuff we are going to discuss, right? Direction of the friction, right? This stuff we are going to discuss. Okay, so guys, this is all about the rotation. This is an entire flow chart, right? Okay, in some of the reference books, yes, it is mentioned, in some of the reference book it is mentioned that the collision is part of the center of mass and every that stuff. But it's okay whether you are dealing that part with the work energy and power, or whether you are dealing here, it's okay, it's not a big deal, right? Okay, it's really not a big deal, because why it has been discussed here, right? Because some of the cases of the motion in that collisions in 2D, right, are the part of the center of mass, right, are part of center of mass, so it is must. Okay, so now I'm moving aside. On the countdown the 5, guys, you can have a snap of it, right? 5, 4, 3, 2, 1, and that's it. Now let's move on to the first most important part of the chapter, right? That is center of mass. What actually the center of mass is, why it is considered. So before moving on to the concept of the center of mass, first of all, let's define what actually the rigid body is, right? What actually the rigid body is. what actually the rigid body is. So it's a very simple thing, right, that I want to show you all, right? Suppose let us take an example. This is a body I'm talking about. This is point A, this is point B, right? So I want to define it as distance between any two particles in body is constant. Distance between any two particles in the body is constant, and that is defined as the rigid body, right? That is defined as the rigid body. In any case, on application of the force, on change in temperature, right, on phasing the friction, on application of any kind of the force or any mechanical force in whatever situation, right, this distance between the two particles, it is not going to change. If we are having the temperature difference between the two ends of the body, nothing is going to be changed. If it is thrown with the velocity v on the rough surface, no configurational changes are observed, right? If any external force is applied, if it is hammered, yes, there is no change there is no structural change in its body. Practically, this kind of the rigid body never exists, right? Practically, this kind of the rigid bodies never exist. But right now, we are not dealing with the practical part. We are dealing with the theoretical aspects, right? So for that purpose, we need to do some assumptions. So this is the assumption, right? Okay, and the definition of the rigid body. In the summarized form, it states that distance between the two particles is always constant. If I want to write, I want to show you all, I want to represent this thing into the very simplified form. The distance between your home, right, and your maternal uncle's home is completely constant. Aapka and Nanihal, distance between them is constant, right? Distance between them is completely constant, right? So in the entire chapter, with whatever structure of the body we are dealing with, right, with whatever kind of a structure of the body we are dealing with, right, we will consider it as the constant, right? Okay, whatever the configuration the body holds, right, it will not change, right, in any conditions, and that will be the rigid body. Now, what actually the center of mass is? Have you ever seen this kind of the situation? A person who is walking on the rope, even you have seen in the teaser also, right? You have seen in the teaser also, right? Okay, you have seen this stuff into the teaser also, right? The person who is standing on the rope, right? Okay, now in this case, I want to tell you all, right? In this case, really, I want to tell you all, okay, see, what actual the definition of the center of mass is, right? So if I want to define it, an imaginary point about which the mass of the entire system is concentrated. Right, and that is defined as COM, center of mass, right? Mass of the entire system is concentrated. First of all, as you all know, entire physics depends on why and suppose. Why this concept was introduced, why this thing was introduced, right? Okay, why this concept was introduced, why this thing was introduced. Most important point. Right, see, if you really want to deal, right, if you really want to analyze the motions of 2D and 3D objects, right, without center of mass, it is quite difficult. Motion is always easily analyzed when we are considering the things at the particle. But how we are going to see? Suppose this is a 2D object, na, right? Now see, it is moving with the constant velocity, na, right? So it is difficult for me to analyze the motion, right? Why? Suppose it is moving with the constant velocity, then in which part of the body I'm going to analyze? Either the front one or the rear one. So it is really difficult to analyze the motion and to get the outputs related to it. So for that, right, suppose let us take an example. I am having the 3D object into my hand, right? Okay, now it is performing the motion. Suppose I am seeing this object from very far distance, then obviously it will be like appear like particle in front of me. But what about suppose let us take an example. I am an observer. I am analyzing the motion. That 3D particle is moving with the constant velocity. The which part of the body is moving with the constant velocity? Even there are lots of structural changes into the body. So I'm not going to get the real outputs in front. I am not going to get the real outputs in front. So in that case, right, the concept of center of mass, why there is a need. So students, whenever you whenever you get stuck in this kind of this stuff, now first of all, right, always have in a always be in a hunt of a need of the topic. Why the center of mass is needed? Why vectors are needed? Right? So to represent the things well into the very summarized form, right, this concept was introduced, right? Okay, so center of mass, let us take an example. What actually let's have the live demonstrations of it. What actually the center of mass is? Mass of the entire body gets shrinked to the specific point. An imaginary point about which mass of the entire system get concentrated gets shrinked. Again, let us take another example. Suppose I am standing into the room. What will be that imaginary point of the center of mass of the room? Right? I am having the wall at front. I am having the rear wall, left side, right side, and the floor and the ceiling. 6 spaces I am having right nearby in my surrounding. Suppose this is a cubicle room, and if I want to find the center of mass, right? What I will do, right? I will try to shrink the entire front wall and gather that mass at one imaginary point. Now the left side of the wall, left wall of the room is getting shrink, right? And it is the mass of the that is getting concentrated at imaginary point. Now ceiling is getting shrinked. Now floor is getting shrinked. Now right. And from the last is a rear wall. So slowly the entire room is getting shrinked and reaching to an imaginary point. And that actual the center of mass is. Right? That actual the center of mass is. Right? That actual the center of mass is. So that's why it is given. And that's why I've given you the example. Na? This is an object. Right? Mass of the entire system get concentrated at one point. This is an object, mass of the entire system get concentrated at one point. And that's the center of mass, right? That's the center of mass, right? Now, basically, why this? See, how it is possible to walk on a thin rope, right? Okay, it is very, so the center of mass concept, right, plays an important role behind this visualization. Right. See, suppose if you are not having that rope, right, the system is completely right. There is a kind of an imbalance produced in that entire system. You're not able to walk on that rope. Right. Okay. But whenever you are, see, you can understand. See, whenever you are holding this rod into your hand, right, you can just analyze this dot. Right. It is getting up and down. Right. Okay, so that center of mass is trying to balance the system so that this person shouldn't get fall from that rope and he can easily walk on that. Right, so that's the right. We are not having that much time to discuss that part into the detail, but yes, the center of mass plays the prominent role behind this phenomena. Now, what actual the classification of the center of mass is? See, basically it is defined for the discrete particles, right, and the discrete particles, they are forming the system. Right. Now we are dealing with the structure, right? So structure, suppose this is a structure, this pan is the structure I'm dealing with. It is a kind of the rod, right? So what will be the center of mass? Obviously in the midpoint, right? But if I'm talking about the micro particles of this pen, can I consider it as a discrete particle? Yes. Can I say the infinite number of the discrete particles are forming the entire system? The infinite number of the discrete particles are forming the entire system, right? The infinite number of the discrete particles are forming the entire system, right? So that's why the first is a center of mass for the the discrete particles. It is for the combined bodies, right? Or you can say for the rigid bodies. We are having some direct formulas. Rigid bodies like center of mass for the semicircular disc, right? Okay. Second, semicircular ring, right? This kind of the structures, right? Hemispheric shell, hollow hemisphere, right? Solid hemisphere. These are the kind of the structure that we are going to deal with this, right? And finally, we are going to deal with the center of mass of the bodies that are having cavities, right? This is the most important part for the mains and advanced level, right? This is things, right, that are kept up to the NEET. The first and second part is kept up to the NEET. The last, the bodies with the cavities, is quite important, right, for dealing the stuff, for dealing the concepts, right? Okay, that will be helpful into the, right, up to the advanced level. Okay, so here dealing with the this cavities, right? Like yes, lots of examples are there. We are going to discuss this stuff, right? Okay. So first of all, let's move on to the concept of the center of mass of the discrete particles. Right? Discrete particle, it means what? Suppose this is a Cartesian coordinate system. So first of all, I want to show you all how discrete particles combine to form this kind of the configuration. Let us take an example for that. Suppose this is a Cartesian coordinate system, right? Suppose this is a Cartesian coordinate system. This is an x-axis, right? This is an y-axis, right? And this is a z-axis. X-axis, y-axis, z-axis. Now what happens here? I'm taking one small infinite particle here. A very small infinite particle. I'm naming it as a dm1. I'm taking another particle on the xy plane. Mass is dm2. I'm taking the another particle on the yz plane. Mass is dm3. I'm taking the another particle. Mass is dm4. Right. So these four individual particles are known as discrete particles. Now this discrete particles with respect to the origin. See, this is an origin. Their position is determined with respect to origin, and with respect to origin, they are forming an imaginary system. See, this kind of the imaginary structure you can obtain like this way, right? This kind of the imaginary structure is formed by four discrete particles. Now, how to locate the center of mass? As I said, first of all, I defined what actually the center of mass is. It is an imaginary point where, right, mass of the system is getting concentrated. So suppose, right, the n number of the discrete particles are forming the system. In this case, 4 number of the discrete particles are forming an imaginary system. The imaginary configuration we are having, right? So where will be the center of mass? At this position, at this position, at this position, at this position. We need to locate that. Right, so entire thing it is about locating the position of the center of mass. Locating the position of the center of mass, right? Locating the position of the center of, right? So this is what just a general idea. Now let's move on to the actual concept and the relevant formula. Suppose first object discrete particle is kept, that is of mass m1. It is kept at the position r1 with respect to origin. Now suppose second object, it is of mass m2, that is kept at position r2 with respect to origin. Suppose third object, it is kept at mass 3 and it is at the position r3, right? Sorry for the interruption. See, it's a very simple thing. Suppose if I'm talking about one discrete particle that is of mass m and it is having position r1 with respect to origin. This is a second discrete particle. This is a third discrete particle, right? Okay, like this, n number of the discrete particles, the infinite number of the discrete particles are forming the imaginary system, right? So can I consider dot, right? This is the mth particle, right? And that position vector of the nth particle is Rn. Like this way, in entire three-dimensional space, right? Enormous numbers of the particles are present. They are forming the imaginary system. How to locate the center of mass for this stuff, right? My first question is how to locate, right, center of mass, right, for this, right? So for that, right, suppose this is a kind of an imaginary system with respect to origin. Okay, so guys, just keep one thing into the mind, right, that I want to demonstrate, or that I want to show you as a note. Center of mass is always, right, calculated with respect to the reference point. It is always calculated with respect to the reference point, always. So that's why we are taken here the origin as the right reference point with respect to which, right, we are going to get the vector, the position vector of that imaginary point. That's center of mass, right? Suppose, how to determine that? Suppose our center of mass is a position, so I'm going to write down the formula, right? It is m1 r1 m2 r2, right, plus dot. If I'm talking about the n discrete particles m and rn, right, whole divided by its m1 m2 dot plus m of n, right? So this is the thing. This is an actual formula of the, right, center of mass, right, where r1 r2 dot rn are the position vectors of the individual discrete particles into the three-dimensional space. Suppose this system is only having the distribute, like suppose, let us take an example, right? This is an x-axis, right? Okay, this is an x-axis, and we are having only the particles that are distributed. Suppose this is m1, this is m2 dot, and this is mn, right? They are situated with respect to the origin at the distance x2, at the distance x1 and x. This is, right, the arrangement of the discrete particles in the entire three-dimensional space. This is arrangement of the n discrete particles only along the x coordinate. So here the x center of mass, it is given as formula m1 x1 dot mn xn, right, whole divided by, that is m1 plus dot plus mn, right, m of n. Okay, so in this case, suppose this is an origin, right, the masses are distributed like this way, right? This is a mass m1, this is a mass m2, and this is a mass mn, right? Suppose the distribution of the particles is going on like this way, right? Then in this case, the, right, center of mass, right, we can locate, right, by this way, m1 y1 dot and mn yn whole divided by m1 plus dot plus m of n, right? Okay, now suppose if, right, if you want to move on to the, suppose, right, towards the z-axis, right, masses are located. Suppose this is m1, right, this is dot, and this is mn. This is, right, z1 and this is zn. So for this, right, the set center of mass, it is like m1 z1 plus dot plus mn zn, right, whole divided by m1 plus dot plus mn, right? Suppose if you want to calculate individual for the discrete particles, right, they are forming the system only on the x-axis, you are having the direct formula, right? Suppose if you want to calculate, right, for the discrete particles that are, right, distributed on the y-axis, you are having the direct formula. Suppose if you want to calculate for the z-axis, you are having the direct formula. But suppose if you want to calculate for the, right, all of the discrete particles that are distributed, right, in the entire three-dimensional system, right, for that we are having this formula, right, we are having this formula, and in this, right, Okay, again I want to mention you all this R center of mass is actually defined as like this way. This R center of mass, that is equal to X center of mass comma Y center of mass comma Z center of mass, right? So by combining these three values, right, we are getting a position coordinate that is an actual center of mass of the system, right? That is actual the center of mass of the system. So whether you are using this formula, it's okay, right? This is a generalized for all of the cases in which the discrete particles are forming the system, right? And suppose if you want to ease the process for the convenient calculations and you are sure about that in the question it has been already given that all of the particles are either distributed on x-axis, on y or z, then we are having these three respective formulas. Okay, so this is what all about the center of mass for the discrete particle is. Directly using this formula, see, in NEET 2021 question has been asked. Right now we are going to solve that stuff. Two particles of mass 5 kg, 10 kg are attached to the rigid rod. This is a mass 1, right, and that is given as 5 kg. This is mass 2, right, this is given as 10 kg. Now they are separated by the distance of, right, 1 meter, right? Okay, now from 5 kg particle, see, from 5 kg particle, it is already mentioned, this is our reference point. This is what our reference point is with respect to 5 kg particle, right? With respect to the 5 kg particle, what is an actual location of center of mass? Actual location of center of mass. See, now you can see the system is the discrete particles are getting distributed on x-axis, right? So if you want to use this formula, it's okay, else you can directly use the formula, right, for the x-axis, and that is m1 x1 plus m2 x2 whole divided by m1 plus m2, and that is nothing else but the x center of mass of the system, right? With respect to this is the reference point, right? What is an x1? Position of the particle, the distance of the particle with respect to the reference point. So for 1 it is 0, for 2 it is 10 into this much distance is 1, right? So whole divided by 15, so that is equal to 2 by 3, and that is equivalent to 67 centimeter approx, right? So from 5 kg, what is an actual location? This entire thing is of the 100 centimeter, right? At the location of 67 centimeter, we are getting the center of mass, that imaginary point of the system, right? At 67 centimeter, right, from the yes, we located the center of mass. C is correct. Now here we are getting the new observation that I'm going to discuss, right? Let's see what actually it is. Suppose, as we saw, this is mass m1, this is mass m2. This was given into the question as 5 kg and this was given as the 10 kg. Why center of mass was not exactly at the midpoint? Generally the students are having this kind of the conception that center of mass, it is a kind of the midpoint, right? Or any, what we can say, the thing that is at the ortho center of the specific object of the rigid body. No, actually it is not a truth. Why? See, this is the midpoint. This is the midpoint. Why actually the center of mass lies here? Why it is shifted towards the 10 kg, right? Okay, so that's the reason I am going in a new note I am going to show you all. For that I need to take one example. Suppose, right, this is mass m, This is mass m, right? They are separated by the some distance r. Center of mass will be exactly at in between, right? So mass of this system and mass of this system that got concentrated at one point, and I can consider that mass as the 2m, the mass of the center of mass. Now, right, let us take the third particle. Okay, let us take the third particle. Suppose this is of the 2m, then center of mass always gets shifts toward the higher mass side, right? Center of mass always gets a shift toward the higher mass side, right? Center of mass is always shifted towards, it's always shifted towards higher mass side. So this is a 2m, this will be the new center of mass of the system. Now suppose on the line joining in particle between two, right, where the center of mass is actually located, I'm taking a perpendicular. I'm taking the third particle, 4m. This is m, 2m, center of mass is here. Suppose it is m, this is m, center of mass is at the midpoint, right? For m and m, the center of mass is at the midpoint, but for m and 2m, the center of mass is shifted toward the higher mass side. Now we are having the new center of mass of the system in the higher. Right, so again the center of mass will get shifted towards the higher side. So this is what we get the actual, right, observation, right, the most noteworthy point related to the center of mass, that it always gets shifted toward the higher mass side. I'm going to show you some examples also related to this. Okay, so now first of all, let's solve these sums related to the basic formulas. Now see, this kind of the question has been asked into the mains 2000, right, in 12. Three masses are placed on the x-axis. See, they are defined. They are all placed on the x-axis, right? They are placed on the x-axis. So it means it is very simple. This is origin. On x, whatever the things are going on, they are going on the x-axis, right? Whatever the things are going on, they are going on the x-axis. Now, 300 gram is kept at the origin. This is only our reference point is 300 gram is kept at the origin. 500 gram is kept at the, this is the mass of the 500 gram and it is kept at the 40 centimeter. And 400 is kept at 70 centimeter. 400 gram is kept at 70 centimeter. Right? Three discrete particles are forming an imaginary system. Obviously, if they are distributed on the x-axis, direct formula with respect to the reference point we are going to take m1x1, m2x2, m3x3, right, whole divided by m1 plus dot 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 plus m3. Right? So what will be the x center of mass? m1, that is 300. Distance with respect to the reference point is 0. Because origin is our reference point and 300 is kept at that position only. Plus, right, we are having another that is 500. It is kept at the 40 centimeter and again plus this one. 400 that is kept at 70 centimeter. 400 into 70, right, whole divided by 500, 400, 900, whole divided by 1200. Right. Now everything is in centimeter and gram only. Right, so we are not going to change that stuff. Right, so x centimeter is 5 into 4, 20, comma 1, 2, 3, 1, 2, 3, 20,000 plus 7 4s are, okay, 28,000, right, 28,000 whole divided by 1200. So 2 zeros are going to cancel, right, so we are having 200 plus 280, right, so x center of mass that is equal to 480 whole divided by 12. Right, okay, to 1240 centimeter. So X center of mass is actually lying at the 40 centimeter with respect to the origin, right? 40 centimeter with respect to the origin. Let me just check it out whether we have done any kind of the calculation mistake or not, right? Okay, so suppose 2 zeros we are getting cancelled, right? Suppose 2 zeros are cancelled here only. Okay, so it's 500, 400, 900 plus 3, 1200 grams. Okay, it's not a big deal. So 40 into 200 plus 70, 280, 480 by 12 years. It's 40 centimeter. Okay, right? So this is what the actual center of mass is. Now, let's move on to the next sum, right? It has been asked into the two. Now we are taking the actual formula, right? The vector form. Two bodies of mass 1 kg, 3 kg, having the position vectors this and this. Okay, see, M1 is 1 kg, M2 is 3 kg. M1 is 1 kg, M2 is 3 kg. What is the position vector of M1? What is the position vector of M2? Position vector of M1. Right, R1, that is equivalent to I plus 2j plus k. Similarly, minus 3I minus 2j, right, plus k. These are the respective position vectors. Now what we need to calculate, right? See, this, if this position vector is given, then obviously it is given with respect to the origin, right? So origin will be our reference point. Origin, if this is a position vector given, na, I, j, k, that kind of the thing, that vector is given, right? So it is with respect to origin, right? And we are going to calculate the center of mass with respect to origin. So here, right, we are decided that we want to keep the right reference point as origin. Now which formula we are going to use? Obviously R center of mass, that is equal to M1 R1, right, plus M2 R2 into the vector form whole divided by M1 plus M2. Right, now, okay, see, it's a very simple thing. Now the R center of mass vector, we are having it as mass is 1 kg, the vector is I, j, I, 2j, k, it's 1, 2, 1 plus it's 3 kg minus 3, minus 2, 1 whole divided by 1 plus 3, that is equivalent to 4. So R of center of mass is 1 minus 9, 3 3s are 9, 1 minus 9 is minus 8, 2 minus 6, that is minus 4, 1 plus 3 that we are having 4 whole divided by 4, right? So the position coordinate of the center of mass of the system with respect to the origin, right, that is RCM. Okay, so that we are having it as a minus 2, minus 1, 1. Right, so if you want to represent this thing into the ijk form, it's minus 2 of I, right, minus j, right, plus k, minus 2 of I minus j plus k, right, minus 2 of I minus j plus k, right. A is the perfect answer for this specific question, right. So this is how we are able to define into the vector form, right. We have seen 3 sums related to it using the very simple formula, right, and right, using that vector form. Now let's move on to the concept of some of the important formulas of the center of mass of the rigid body. As usual, this was about the discrete particles, but what about the rigid body? Okay, first of all, allow me to drink the okay, rigid body. What actual the rigid body is, as you all aware of, I told you all about the definition. Let us take an example to understand this. Suppose this is a ring-like structure, right? This is the ring-like structure. Okay, we are having the radius as equal on the all sides, right, like this way you can consider, na, right? R is equal because it's a perfect circle, right? Now in this case, I want to tell you all, mass of the system is getting concentrated because see, suppose let us take an example. If you're considering the small discrete particles, this is the first particle, this is the second particle, right? This is the third particle, right? And this is the fourth particle, right? This is the fifth particle. Like this, we are having the n number of the particles, they are distributed, right? The mass is distributed, right? Okay, and we are getting this stuff. Now in this case, this is our center of mass. I'm going to show you all the new stuff. If all masses are identical and they are uniformly distributed, then the center of mass is going to be at the midpoint. If all masses are identical and uniformly distributed, then we are going to have the center of mass at the midpoint. Then we are going to have the center of mass at the midpoint. What happens if the configurations get changed? Let's change the configuration, right? Suppose if I am cutting the half part of the ring, as I said you all, center of mass always shifts to the higher mass side. Suppose, let us take an example. This is an x-axis. This is a y-axis. In this case, with respect to x-axis and y-axis, right? Just fold the object. Fold the object. We are getting the mirror images on both sides, right? If you really want to understand this concept, right? Okay, you can just fold the object with respect to the x-axis, fold the object, sorry, with respect to the y-axis, fold the object with respect to the x-axis. On the both, with respect to both axes, the mirror images are formed. That's why we are having the center of mass at the origin. In this case, with respect to y-axis, mirror images are formed. With respect to y-axis, mirror image is formed. If with respect to y-axis mirror image is formed, no shifting on x-axis. It means position coordinate of the center of mass on the x-axis is going to be fixed. But you can see with respect to x-axis, right? With respect to x-axis, no mirror image is formed. No mirror image is formed. With respect to x-axis, no mirror image is formed, right? The mass of the system is on the upper side. Lower we are having no mass, because we have removed the half part of it. So for in this case, obviously the initial center of mass of the system was this. When half the lower part of the ring is get completely cut or removed, right? So it means this center of mass is going to shift towards the higher side. So if with respect to if with respect to y-axis mirror image was formed, no shifting on x. With respect to x-axis, mirror image is formed, no shifting on y. That's why the center of mass of the original configuration was at the midpoint. No shifting. But here, with respect to y-axis, mirror image is formed, so no shifting on x. But with respect to x-axis, no mirror image is formed. We will be having the shifting on y-axis. This will be the new center of mass of the system. Right? New center of mass of the system. It got shifted towards the upward point. Now suppose if I want to cut again the quarter part of the ring, now what will happen? See, this much part is cut. Whole system, center of mass at the midpoint. Half system is cut, center of mass shift towards the higher side. Now another quarter part of the system is cut. Neither, say in this case, mirror image is formed with respect to x-axis also, no shifting on y. Mirror image is forming with respect to y-axis also, no shifting towards the x. So that's why center of mass is at the midpoint. In this case, mirror image is forming with respect to y-axis, no shifting on x. But mirror image is not forming with respect to x-axis, so center of mass shifted towards the y. In this case, no mirror image is forming, neither with respect to x-axis, no y-axis. So in this case, we are getting right shift in with respect to x-axis also and y-axis also, right? So this will be right. First of all, right, the center of mass got shifted to this part when it was a quarter part of the ring. Now it got shifted to this, the higher mass side. So this is a new center of mass of the system. Right, the new center of mass of the system, right? So this is how the center of mass for the rigid bodies it has been calculated. This is having some specific value, y is equal to something, right? And we are having the specific formula for this also, right? Like formula for this is the r, if you want to determine is x center of mass, that is integration, right, of dm, it's dm of x, right? A long derivations are there, right? Okay, a long derivations are there to calculate the right center of mass for the semicircular disc. First of all, right, semicircular ring, right? Second, semicircular disc, right? The third one, lots of things are there, right? Lots of rigid bodies are there, right? Okay, hollow hemisphere, right? The next one, right? Okay, the solid hemisphere, right? But we are not going to move on to the derivations related to that, right? Because for JEE and NEET purpose, right, only formulas are needed. Okay, so now this is what the actual formula is, right? This is what the actual formula is, right? Okay, see, semicircular ring, this is x-axis, center of mass shifted to 2r by pi. Semicircular disc, this is x-axis, right? This is y-axis, right? Okay, for hollow hemisphere, right, this is y-axis, again this is x-axis, it has been shifted to r by 2. For solid hemisphere it is 3r by 8. For solid cone it is h by 4. For hollow cone it is h by 3. For triangular plate is h by 3 with respect to base. So these are some direct formulas. But for this, three most important densities are needed. These three densities we have already discussed into the previous sessions, right? Okay, these three densities we have already discussed into the chapter of NLM. To determine the center of mass of this kind of the objects, right? To determine the center of mass for this kind of the object, first of all, again I'm going to define those, right? Okay, the first one is the linear mass density. Linear mass density. How mass is distributed over specific length of an object. how mass is distributed over specific length. Second, right, for rod we are also having that surface mass density. Second one, that is surface mass density, right? Sigma is equal to mass per unit area. How mass is spreaded over area. The third one is volume mass density. This is a general definition we are using into our, right, all of those calculation. How much mass is contained in a volume. How much mass is contained in a volume. Mass spreaded over length, sorry, mass distributed over length, mass spreaded over area, mass contained into the system. The three different words are there and they are in of the actual sense. Mass distributed over length, mass spreaded over area, mass contained into the volume. Right? We are going to take the lots of examples, right, using this formula, right? Okay, we are going to use this formula, that is x center of mass, that is integration of, right, x into dm whole divided by integration of dm, right? We are going to use this formula and we are going to solve, right, many sums, right? Okay, now in this, right, we are going to have, right, the center of mass, two bifurcations are there. Center of mass for the combined bodies, right, and center of mass for the bodies with the cavities. Now let's move on to that part. Combined bodies. Very simple example here we are going to take. Very simple example. Some of the examples, right, we are going to take, right? Okay, and before that, okay, let's move on, right, to the simple case of a rod. Suppose this is a rod, right? With respect to origin, I need to calculate the, right, center of mass of the system. Lambda is constant, length is L. Lambda is constant, it means mass is uniformly distributed. Same formula I'm going to use, x center of mass, that is equal to integration of dm into x, right, whole divided by integration of m. To calculate the center of mass for the rigid bodies, always elemental masses are needed. Suppose if it is a rod, I am taking a small elemental mass, right, dm, right, it is at the distance x, right, it is at the distance x, right. Now suppose this is a dm, lambda is constant, can I say lambda that is equal to dm whole divided by dx, right, and that is equal to mass per unit length. So can I say dm that is equal to mass per unit length into dx? Can I replace it here, right? That is mass per unit length into dx into x whole divided by integration of mass per unit length into dx, right? So x of center of mass, now what will be the limit? From what point to what point x is getting varied, right? In between what, like in between the limits, in between the what values of the limits, this x's value is getting changed. Obviously it is going to change from x is equal to 0 to x is equal to L. So the limits will be kept as from 0 to L, from 0 to L. So x center of mass, obviously this will be m by L will get constant and it will be out, and this is m by L integration of x dx limiting from 0 to L, integration of dx limiting from 0 to L. Right, so resolving this, we are going to get L by 2 as the center of mass of the rod, right? This will be the center of mass with respect to the reference point, that is an origin, exactly at the center. Suppose this is what we define, like this way for semicircular ring, using the same formula it is defined, right? For the semicircular disc, for the hollow hemisphere, for the hollow, right, a solid hemisphere, right? Okay, all of these things, right, they are getting defined like the same way. Just the elemental mass are getting changed. In this, we have taken the small elemental mass, right? In the ring, we are going to take small. In the disk, we are taking the ring as the elemental mass. In the hollow hemisphere, we're going to take the ring, right, as the elemental mass, right? In the solid hemisphere, we're going to take the hollow hemisphere as the elemental mass, right? Okay, just this structure, right? The way of defining the elemental mass gets changed. Now, suppose we are taking the another example. This is a rod. Mass is non-uniformly distributed. How we are going to locate the center of mass for that? Mass is non-uniformly distributed, then how we are going to locate? Non-uniform distribution, it means lambda is directly proportional to x, or lambda is equal to lambda 0 of x. For that also we are going to have the same concept. Again, I'm going to take the elemental mass, right? It's with its dx and it is situated at the x distance with respect to the origin, right? What will be the center of mass? That is integration of, right, dm of x whole divided by integration of dm, right? Now, lambda is equal to mass per unit length, right? So can I consider dm, that is equal to lambda, right, into dx, right? So dm, that is equal to lambda 0x dx, right? The elemental mass, we got that. Okay, now I'm replacing all of those values, right, to get the answer. Okay, so x center of mass, that is equal to integration of lambda 0, right, x square dx, right, whole divided by integration of lambda 0x dx. Like this lambda 0 is going to get cut. Okay, the limits will be from 0 to L, 0 to L, right? So this will be x cube by 3 whole divided by x square by 2, limiting from 0 to L, right? So finally we are going to get the distance that x center of mass is at, okay, 2 by 3 L cube by L square. So x center of mass, that is equal to 2 by 3 L. See, on the non-uniform mass distribution, right, we are getting the new center of mass of the system as 2 by 3 L. I'm sorry, it wouldn't be here, right? It would be somewhere here, right? So mass was uniformly distributed, it was exactly at the center. We are having non-uniform distribution of the masses, right? We got the new answer. Suppose if these equations get changed, the location will get changed. This equation is going to change, like suppose lambda 0x square, right? So that shows how mass is distributed on over the entire length, right? Those things are getting changed, right? So this is what actual about how to calculate the center of mass for the rigid bodies. Right now, let's move on. If you want to take a snap, it's okay. Combined bodies. Suppose if I'm taking particle m1, that is equal to 3 kg, right, m2, that is equal to 5 kg, right, length of m2 is 10 meter, right, mass is uniformly distributed. In another sense, I want to tell you all, lambda is constant. How to define the center of mass of the system for this configuration? Suppose this configuration is given. How to define the center of mass for this? Now see, suppose these are the rigid bodies. This is a particle. This is not an exactly sphere, right? But it is a particle. Let us consider it as a particle of this mass, right? Suppose it is a particle. If it is a sphere also you can solve, but at the beginner's level, right, we are going to consider it as a particle. Now we are going to use a simple formula. See, mass is uniformly distributed. It means it's very simple. We are going to take m1 x1, m2 x2, right, whole divided by m1 plus m2. Right? Okay. Now, for this, using this formula, dm of x, integration of dm, we already calculated the center of mass as L by 2. This is a rigid body. Yeah, we can consider this as a particle, right? But this is a rigid body. For this, we have already located the center of mass using this formula. And we got as L/2 as you all seen before. Right? So for individual rigid body, we can use this formula. For the combined system, we need to use this. Because in a combined system, more than one masses are always there. Right? So now, mass 1 is 5 kg. Sorry, mass 1 is 3 kg. What is the distance of 3 kg with respect to the reference point? Obviously 10 meter. Plus. Mass of 2 is 5 kg. Whenever you are considering the rigid body, distance between center of mass and reference point is always considered. This thing we have discussed into the chain problems of the rigid body also. Because we have introduced the concept of the center of mass. So right now we are considering the mass of the entire system get concentrated at one point. Mass of the entire system we shrink at one point. Now we are having the system like this way. M1, M2 is here, M1 is here. Because mass of the rod gets shrinked at that imaginary point, and that's why we have used this formula. And this is only the easy way, right? Okay, so this will be 5 meter. Okay, this will be 5. So to just consider one point, whenever you are calculating the center of mass of the rigid body, distances are always calculated with respect to the reference point. Distances are always calculated in between reference point and center of mass of the object. Right? So the x center of mass, that is equal to 30 plus 25 whole divided by 15. So that is 55 whole divided by 15. So 5 3s are 5 11s are. So x center of mass, that is equal to, right, 11 by 3. Right. Let's take another example. Right. Let's take another example. You don't get so much worried. To calculate the center of mass for the combined body, suppose this is a square, right? Length is L. A disc is kept, right? A disc is kept. Okay, disc is kept. Right, of L/2 radius, right? Diameter is going to be L, right? We are having one disc. Suppose this is given, we need to calculate the center of mass for the combined systems. Now how we are going to calculate that stuff? For that we need to first of all we need to have a reference point. This is the reference point. Using the formula integration of dm of x by integration of dm, we have already calculated the center of mass, right? For this also we are having the formula of the center of mass. Yes, all of the masses are uniformly distributed over it. So directly we are going to calculate the x center of mass, sorry, this time y center of mass, that is m1 y1 plus m2 y2 whole divided by m1 plus m2. Now here the question arises, masses are not given. Dimensions are given, masses are not given. So first of all, we need to calculate the masses, right? Okay. Many students are in confusion why the concept of linear densities, linear mass densities, right, surface mass densities and volume mass densities were introduced. Why? So I'm going to tell you all the reason behind it, right? Okay. The center of mass, right? The reason behind it is, first of all, we need to calculate the mass. Suppose this is a 2D object, right? So this is right, see, lambda is constant for both. So this is mass per unit area. Suppose if I am doing for a square, so this is a mass of a square. What is the area of the square? That is L square. So mass of the square, that is equal to sigma into L square. Consider this as equation number 1. Mass of a disk, mass of a disk per unit area. So mass of the disk, right, that is equal to sigma. Both are of the same material, that's why sigma is kept constant, right? So it is pi L square by 4. right? Using the densities, we can calculate the masses. Now we are going to calculate the center of mass of the system. So y center of mass, that is equal to m1 y1 m2 y2 whole divided by m1 plus m2. If we are considering this as a reference point, then what is the mass of 1? That is equivalent to the sigma L square. This was a mass of square. Distance is 0. What is the mass of disk? Sigma pi L square by 4. Now what is the actual distance between this part? Right. As I said, now distance between the center of mass of the rigid body and reference point. For disk, center of mass is at L by 2. Right. Reference point is here. So it's L by 2 and L by 2. Distance is L. Whole divided by sigma pi L square by 4 plus sigma L square. Sigma, 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 we are going to get cancelled it. Y center of mass, that will be equivalent to, right, pi L square by 4 into L whole divided by pi L square by 4 plus L square. L square is gonna cancelled. Right, so finally we are going to get the y center of mass of the system, right, as, okay, suppose we are cancelling the 4 also, so it's in the bottom it is pi plus 4, and at the top, right, we are having pi of L. This is the center of mass of the system with respect to this reference point, right? So this is how. See, in the previous cases you are aware of, see, masses are given, we can directly apply that formula. But if masses are not given, dimensions are given, then we need to take help of mass densities, right? We need to take help of the mass densities, right? Like this way, lots of things we can calculate. Right, by own, to clear the concepts of center of mass. Suppose this is a disk of radius r, another same disk is kept of the radius r by 2. Right, now what will be the actual mass of the system? Right, mass of the whole disk, sigma is equal to mass by area. Mass is equal to sigma into pi r square. Mass for the lower part, the smaller disk, it is sigma into pi r square by 4, it is m by 4. We got the masses m by 4. Now it is easy to calculate that stuff, right? Okay, like this way you can move on. Okay, so this was the center of mass for the rigid bodies, right, with the respective formulas. Now it comes the most important concept, right, the center of mass of the cavities. Whenever the cavities are blown out, right, how to calculate the center of mass for that? It's a bit different procedure, right? But as usual, it is easy. Don't get so much worried about it. Right, center of mass for the cavities. What actually the cavities means? Some part is removed from the rigid body. Right. Suppose this is a disk of the radius r, right? A cavity of radius r by 2 is removed. Now what actually the center of mass of the system is? The new center of mass of the system. Right, this one examples of the cavities I'm going to show you all, and one example I'm going to show, right, I'm going to give you all in the homework, right? One example I'm going to show you all in front, right, and one example I'm going to give as a homework. Now see, again we are not having the masses. So whenever in the case of the rigid bodies you are not having the masses, don't get so much worried. First of all, just identify the masses using the right mass densities and then apply the concepts, right? Okay, first of all apply the concepts of mass densities, right? Okay, see now, suppose if I'm talking for the whole disk, sigma is constant for both. If you want to take right, if you want to increase the complexity level, right, okay, and make that sum quite complex, you can change the value of, right, sigma. Sigma is constant for both. Sometimes, right, okay, it is taken, this is a sigma, a new 2 sigma is added, right, lots of things are that, but in that case only the mass is going to change, not, right, okay. So suppose if this is a sigma constant for both, so sigma is equal to mass for the system by area, right? So mass we are going to get sigma into pi r square for the whole system. Can we consider this is equation number 1? Yes. For the cavity, can I say mass of the cavity, that is sigma into area of cavity? Array, I'm sorry. Sigma is equal to mass upon area, mass of cavity, area of cavity. So mass of cavity, that is sigma into pi r square by 4. So replacing this value, I'm getting mass of cavity, that is equal to m by 4. What is the mass of remaining system? That is mass of whole system minus mass of cavity, 3m by 4. Right, we got the mass of cavity as m by 4. We got the mass of the whole system as m, and we got the mass of the remaining system as m by 3m by 4. Now, how we are going to deal with the formulas of center of mass? Again, let's take this. Suppose m1 we are taking mass of cavity, m2 mass of remaining system. If we are taking m1, see, if we are going to take m1 as a mass of the whole system and going to minus that stuff, I think that is thing not going to work. Suppose if we are considering this as the reference point and the origin 0, 0, right? If we are considering m1 as a mass of cavity, mass of remaining system, both combined, both two individual systems are getting combined to form the whole disk. And for, see, I'm talking about the two individual systems, one cavity that has been removed, one remaining system. If I'm combining both this stuff, I'm having the whole disk, and the center of the mass of the whole disk is 0, 0. So this is mass of cavity, distance, mass of remaining system, distance, whole divided by m1 plus m2. This procedure, if you are following, right, quite complex sums you are going to solve into the very less amount of the time. Just consider the two individual systems. See, center of mass of the whole systems lies at 0, 0. Just consider the two individual system, one cavity, remaining. Combine these two things, we are getting the whole system, and the center of mass of that whole system is at the origin. Things will get cancelled out easily. So we are getting what is the mass of the cavity, that is m by 4. Now what is that distance of a cavity with respect to the reference point? See, cavity we have plugged out, it is a rigid body. So obviously the distance of the center of mass of the rigid body with respect to the reference point is calculated. So it is m by 4, distance is r by 2, is equal to minus 3m by 4, right? Okay. Now suppose it is getting shifted to x, right? The center, the new center of mass of shifted is shifted to x, and we need to calculate that value. So x is equal to negative r by 6. Negative, it means with respect to origin it is shifting towards the left side, right? So what is the center of mass of the new system? See, it's very simple, right? Suppose this is x-axis and this is y-axis. uniformly distributed. With respect to x-axis, mirror images are formed. With respect to y-axis, mirror images are formed. Everything is getting but. Suppose this much part is removed. Now with respect to x-axis, mirror image is formed. It means no shifting on y. With respect to x-axis, right, mirror image is formed. So no shifting on y. But with respect to x-axis, mirror image is not formed. Sorry, with respect to y-axis, I'm sorry, right, no mirror image is formed. Right, it means we will have a shift on x. And that is a shifting on x. And this will be the new center of mass of remaining system R by 6. So this is the procedure to calculate, right? Yes, I can understand it is difficult to adapt this procedure at the very first. When you see this stuff at the very first moment, it is difficult to adapt this, right? So for that reason, I want to advise you all to just rewind this video and see this concept again. Like this way, from any object you can take any kind of the actor. Like suppose I'm going to give you all a homework, right? Suppose this is a square plate, right? Right, this is a square plate. Semicircular disc is cut. Right, this much part is removed. I'm sorry. Length is L. This is a cavity. Right, this is a cavity. The same thing here. Suppose you are going to use formula m1 x1 m2 x2, right, whole divided by m1 plus m2, right, is equal to, right, center of mass. If you are considering m1 as a mass of cavity, m2 as the mass of remaining system, combining both, we are getting the whole system, right? And the center of mass of that part is 0, 0. In this also same, m1, you have to identify the mass of cavity. Okay, the radius is L by 2, right? Again, the dimensions are given. It means you have to move on for the masses, right? In this, you just keep one thing into the mind. Distances from the center of mass with respect to reference point is calculated. This is our reference point. This distance we have seen in the formula. Suppose it is a disk, na? See, this distance we have seen. For a disk, it is 4r by 3 pi. Semicircular disk. This distance is 4r by 3 pi. Now see. This is 4r by 3 pi. This is L by 2. So it is L by 2 minus 4r by 3 pi. So it's L by 2 minus 4 into L by 2 into 3 pi. This will be the distance of center of mass of cavity up to the reference point. So whenever you are going to consider the mass of the cavity as m1, right, we need to consider this much distance, and this one is, right, the things I have resolved, you have to just calculate, right? And this is a homework from my side. I think maximum part I have resolved, right? But still, right, the calculation part is quite lengthy, right? Okay, so I'm keeping that in front. Okay, so this is a homework from my side. You can just keep this. You can answer this homework beneath the video, right? You can answer this stuff beneath the video, right? So this was the center of mass of the cavities, right? Okay, now motion of the center of mass. It's a very important thing, right? Till now We have located the center of mass. But this time we are going to understand the motion of the center of mass. We are having the visualizations in front. Suppose, let's take an example to understand. Suppose this is a ring kind of structure. 2 beads are kept. Right. One is of mass m, second is of mass m. What will be the, see, till now we have seen the location, right? We located the center of mass, right? Now we are going to understand the motion of center of mass. Till now we have understood, right, the concept of center of mass. Now we are going to understand the motion, whether the center of mass is moving or not. Right, let's analyze the simple example. This is m, this is m. Center of mass is at the midpoint. This is m, this is m. Center of mass is at the midpoint. Okay, now see, suppose, just you can just imagine, center of mass is moving or not. If both of the hands, right, are moving into the opposite side with the equal velocities, right, the center of mass will remain at stationary at that point. Right, now let us take another example. This is m, this is m. Center of mass is at the midpoint. Right, now only this particle is moving with a velocity v. You can just imagine the center of mass is also moving towards the right side. That's the motion of center of mass. Suppose this is m, right, and this is the center of mass. Now this is moving. You can just imagine the center of mass is moving towards the left side. Let us take another example. Right, this is m, center of mass is at the midpoint. Okay, now this is moving with v and this is moving with 2v, or this is moving with v, this is moving with 2v, right? Okay, so this is moving with v, right? Then also you can see the center of mass is moving, but towards the particle that is having higher velocity. Location of the center of mass is towards the higher mass side. Similarly, the velocity of the center of mass is always towards the particle that is having the higher velocity or higher mv, right? Okay, so it means yes, the center of mass is moving. Let's have another example. Bit of mass m, another bit of the mass m. See, this is the center of mass. Suppose the motion is starting at t is equal to 0. After some time, one bead is reaching here, second bead is reaching here. What will be the what will be the position of the center of mass at time t1? This is a new position. At time t2, particle is at here, this is at here. What will be the new position? At t is equal to 0, center of mass was here, and then it became here, then it here. Now, at t3, m is here and m is here. Center of mass. See, center of mass is going to be at the midpoint. Finally, we are going to reach here mm. Center of mass will be here, and they will just interact. Center of masses. What path the center of mass followed? Straight line. In between initial and final points, did we saw any kind? Did we found any kind of the motion of the center of mass? Yes. It was along the straight line. It was along the straight line. Now let's take another example to understand this stuff into the detail. Right now. Mass m, mass m. Both are scrolling down with the velocity. What is an initial position of the center of mass? Suppose after some time mass is here, position is here. After some time m is here, position is here. After some time m is here, right, m is here at the different time intervals, right? Position of the center of mass is here. So at the final stage m is here and m is here, position is So in between t is equal to 0 to t is equal to time t, when journey is completed, whether center of mass moved or not. Yes. It gained some velocity. Yes, it gained some velocity. What path it followed? Straight line. Formula of the center of mass is R center of mass, that is m1 r1 plus dot 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 plus mn rn, right, whole divided by m1 plus dot 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 plus mn. Differentiating this equation, right, with respect to time, right, we get velocity of the center of mass, and that is m1 v1, right, plus dot 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 plus mn, right, vn, whole divided by m1 plus dot 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 plus mn. This is what the velocity of the center of mass is. If it is constant, I'm sorry, it is constant, right? It is constant. I'm sorry. Okay. Suppose in the previous case, in this case, it's not a big deal, right? This cases were just to tell you all, just to make you all imagine that yes, there is the motion of center of mass, right? Whether the particles are getting accelerated or not, it is also important. Here in this case, particles are only having the different velocities, right? Velocities of all particles are constant. So that's why we are getting the constant value of the velocities of center of. But let's differentiate again with respect to time. We are getting the acceleration of center of mass as m1 a1 plus dot 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 plus mn an, right, whole divided by m1 plus dot 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 plus mn. This is the acceleration of the center of mass. This is the equation of the velocity of the center of mass. M center of mass is at the midpoint. It is moving with the constant velocities, right? Then the things will get limited up to this equation. Suppose any one of them particles are getting accelerated, then the center of mass will also get accelerated. So basically we have dealt with the two kind of motions, right? We have dealt with the two kind of the motions. The first one, a uniform motion in which the velocity of the particle is getting constant. So it's a simple, na? Velocity of the center of mass is constant, right? If the velocity of the center of mass is constant, can we say the center of mass is performing the uniform motion? If velocity of the center of mass is either increasing, right, or it is decreasing, or in another sense, acceleration of center of mass is constant, right? So can I say the center of mass is performing, right, a uniformly accelerated motion? Right, uniformly accelerated motion. We are going to see all of those examples also. Don't get so much worried, just understand this concept. Suppose acceleration of the center of mass is constant. Yes, we can use this equation. What? S center of mass is equal to initial velocity of center of mass plus half the three equations of motion. V center of mass is equal to u center of mass plus a center of mass into t. Final velocity of center of mass minus initial velocity of center of mass is equal to 2a center of mass and distance covered by center of mass. This is what actual the motion of the center of mass is, right? This is what actual the motion of center of mass is. to understand the motion of the center of mass, it is important to understand how to locate it, right? Okay, I think 1.5 hours of the lecture has been gone in this concept. Okay, still there are some things, right? After this we are going to discuss moment of inertia. Okay, but there are some things. Okay, see now, let's see the sums related to it. Some sums. Suppose, very simple, m1 that is moving with 5 kg, this is of 5 kg, m2 that is of 10 kg, right? This is having the v1 as 10 of I meter per second, and this is as v2 that is equal to negative of 10 of I meter per second. What will be the velocity of center of mass? These are the direct formula based question, that is m1 v1 m2, right, v2 vector whole divided by m1 plus m2. You have to consider the sign conventions in it, right? So it is 5 into 10, right, minus 10 into 10, right, whole divided by 15. So this will be 50 minus 100 minus 50 by 15, right? Okay, so 5 tens are 5 3s are, it's minus 10 by 3 I meter per second. What is the velocity of center of mass? Right, it's minus 10 by 3 of I meter per second. These are direct formula based question. Accelerations are given, right? Velocities are given. This is the velocity in 1D. The vector is in 1D. Okay, sometimes 2D equation is given, 3D equation, and lots of things are given. Right. Suppose if I am going to give the acceleration of this, then you are going to apply the direct formula of the acceleration. That acceleration of center of mass is m1 a1 plus dot 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 mn an, right, whole divided by m1 plus dot 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 mn, and you are going to get the answer. But things are getting changed, right, when new concepts are introduced. Suppose in this, right, you are going to understand, right, the concept of center of motion or the center of mass into the more appropriate manner. Suppose this is of 4 kg, right, this is of 6 kg. Initially they are at the same level. Question states that in t is equal to 3 seconds, what will be the distance covered by center of mass? Nice question. Now, suppose this is 4 kg, this is 6 kg. We are completely aware of this 6 kg is going to accelerate with the net acceleration into the downward direction, and that is going to accelerate with the net acceleration into the upward direction. Right, and we are going to calculate the net acceleration. We are having the direct formulas also, or with this kind of the sums we have seen into the NLM, that is 6 minus 4 by 10 into 10, right? So the net acceleration is 2 meter per second square, right? Or you can take it as g by 5, right? Now this is 4 kg. It is moving downward, sorry, this is 4 kg, right, and it is moving upward with the acceleration g by 5. This is 6 kg, right, and it is moving downward with the acceleration g by 5. What will be the acceleration of center of mass? It's very simple. Acceleration of the center of mass is, right, m1 a1, okay, m1 a1 plus m2 a2. It's m1 a1 vector, right, plus m2, right, a2 vector whole divided by m1 plus m2, right? What is mass 1? 4. Acceleration is 2 plus mass 6. Now if you want to take upward as positive, according to the convention we are taking upward as a positive and downward as negative, right? So 6 into minus 2 whole divided by 10. So 4 2s are 8, right, minus 12 by 10, so it's minus 4 by 10, right? It's minus 2 by 5. The acceleration of the center of mass into the vector form is minus 2 by 5 of j into meter per second square, right? We got that, na? whether the motion of the center of mass is this, right? The acceleration is constant or not. See, acceleration is not there, center of mass is performing the uniform motion. Acceleration is there, it is a case of the uniformly accelerated motion, right? So if you want to calculate the displacement, it means you need to use this formula. We got the acceleration of center of mass. Yes, we got that. What we need to calculate in 3 seconds, how much distance it is covered. So displacement takes displacement of the center of mass, that is initial velocity of center of mass of t plus half acceleration of center of mass into the t square. This same equation we are going to take into the vector form. Initially, when they both were at the same level, the system was at the rest. This part is 0. So the displacement vector, it is half. Acceleration vector is 2 by 5, right, into t square. T square, it is 9. Okay, it's negative of j. So what is the displacement? What it states, the displacement vector state 2 is going to cancel. That is negative of 9 by 5, right? Okay, negative of 9 by 5. Okay, this is what the displacement, right? This is negative of 9 by 5 j meter per second. Sorry, only meter, right? It's only meter. Okay, this is the displacement. Magnitude of the displacement is distance, right? Magnitude of the displacement is distance. So distance is 9 by 5 meter. This is the distance traveled by the center of mass into the 3 seconds. If I want to confuse you all, right? If I want to confuse you all, (6 kg, 4 kg. Calculate the acceleration of the center of mass, and in 1 second, how much distance is it getting traveled? Simple. Net acceleration, it is in downward direction. Here the net acceleration into the right side according to the Newton's law. Right, from this we are getting the equation 6a is equal to 6g minus t. And here we are having 4a, that is equal to t. Right, so 10a, that is equal to 6g. So a is equal to 6g by 10, right? So it is 3g by 5. Now obviously it is going to 6 meter per second square, right? Okay, this t is gonna cancel. Now acceleration of the first particle, it is in downward direction, so it will be negative of 6 of j meter per second square. Acceleration of the second particle is towards the right, so it is positive of 6 of I meter per second square. In this, we are going to get the acceleration of center of mass m1a1, m2a2 into the vector form whole divided by m1 plus n2. m1 is 6 into 6 of I plus 6 into negative 6 of j and 4 into 6 of I whole divided by 10, right? So we are going to get it as negative 36, right, of j, okay, plus 24 of I whole divided by 10. So it is equal to negative 3.6 of j plus 2.4 of I. This is of the acceleration of the center of masses. This is also constant, but in the previous case, I'm sorry, yaar, it is gone. It was a black screen. In the previous case, we were having that in 1D. In this case, we are having it into 2D. So what will be the acceleration of center of mass is negative of 3.6 of j plus 2.4 of I. In 1 second, right? The displacement vector, initial velocity is 0, it's half. Right, negative of 3.6 plus 2.4 j plus I into t square is 1, right? So the displacement vector we are getting it as 1.2 of I minus 1.8 of j. This is the displacement vector for the center of mass. Magnitude of this, right, is the distance, right? That is 1.2 square plus 1.8 whole square. So this is how the motion of the center of mass is analyzed. right? Motion center of mass is always having the motion as because of the external forces, not as because of the internal forces. Center of mass is always having the motion as because of the external forces, not as because of the internal forces, always. Right? For internal forces, we are not going to discuss that much part, right? You all are aware of this example, right? Okay, first I want to write down the statement, right? The motion as of internal forces, the state of rest or state of motion of center of mass COM is not going to change. As of the internal forces, the state of the center of mass is never going to change. Let's take an example of it. You all are aware of this. This is a rod, right? And a man is standing at one edge. Rod is of length L, mass of man is M. Right? Suppose it is going on from this position to this position. Suppose a man is moving from A to B. What is the displacement of Planck? Right? But man is moving, right? It is getting displaced with respect to Planck. Right? So we are having mass of man, that is M1, M1 plus M2, that is displacement of man with respect to Planck. Suppose he is moving with velocity v with respect to Planck. Let's differentiate this equation with respect to time. We get velocity of a Planck, that is m1 whole divided by m1 plus m2. V relative, again differentiating. Suppose the person is getting accelerated, so the acceleration of the Planck, right, that is m1 whole divided by m1 plus m2, right, a relative. This is all thing you are all are aware of, right? Just keep one thing into the mind here, what actual the concept is, right? What actual the concept is. The concept states that, right, as of the internal forces, right, the center of mass is not going to change. See, suppose person was standing here. This is the center of mass of the rod. This is the center of mass of system. If the person is, let us take an example, person stands, okay, person is moving towards the left side, so obviously the Planck is going to displace. Suppose if the person reaches the right side, this is a C. You can just check it out. Center of mass, the initial position of the center of mass of the system, the final position of the center of mass of the system, right? It is same. It is lying on the same line. Why? Person who is running on the Planck, it is not applying the external force. I'm talking about the entire system, external force is 0. So whenever the external force is 0, center of mass is not going to displace if it at rest. And if it is in motion, it is not going to change its state. It's very simple. If external force on system is 0, net external force, center of mass is not going to change. This state. Let's see questions on this. Okay, see, the question on this concept has been asked in 2012. Two persons of mass 55 kg and 65 kg are at the opposite end of the boat. There is one boat, right? Okay, this is here, it is a person of 55 kg right? And here the person is standing for 65 kg, right? Okay, the plank weighs 100 kg. Plank weighs 100 kg. Now both are moving right nearer to each other. If boat is in still water, the center of the mass shifts by. Boat is in still water, the net external force on the system is 0. Whether the center of mass is going to shift of this system? No. Correct answer is 0. So students, I think let's move on to the concept of moment of inertia, right? Okay, what actually the inertia is. See, if you want to understand this concept into the most convenient manner, right, then I want to remind you all that we have seen the definition of the inertia into the previous lectures, right, in NLM. Right, the property of a matter that resists the change, right? The property, right, of matter that resists the change. Right. In another sense, right, if you are aware of, we defined it as a taklif. In Hindi, it is right, a taklif. What kind of a taklif? Right, the taklif in another sense, whenever suppose I am at rest, right, I don't want to change my state, but suddenly, as of some external forces acting is applied on me, right? Okay, so as because of that, I need to change, right? I am forced to change my state, right? So at that moment, right, the property of an object that is acting on, right, and that is defined as inertia. So taklif, right, taklif in changing its state. But here when we were talking about the inertia, right, then we were talking about the translational motion of an object. Translational motion of an object, but in this case we are dealing with something else, right? Moment of inertia. If I'm talking about the rotational motion, a very simple example I'm going to give you all. If I'm talking about the rotational motion, for translational motion, the property of an object that resists the change, right, is inertia. But in rotational motion, the property of an object that resists the change is moment of inertia. Is moment of inertia, right? It is moment of inertia. See, it's a very simple stuff. Let's compare this. Let's understand this by one example. See, this is an object of mass m, right? It is moving with the constant velocity into the forward direction, right? Or let's right, make it the acceleration of the system as constant, right? Acceleration of the system is a constant. So can I say this particle is performing the translatory motion, right? Okay, it is a motion, right, along the straight line or along the straight path, right? Now let us take an example. See, suppose if here the acceleration is constant, it means the velocity is either continuously increased or uniformly it is getting increased or uniformly it is getting decreased. Suppose let us take in another example, right? This is a disk, right? This is the disk. A particle at an edge of the disk, right? A particle at an edge of the disk. It is performing the rotational motion like this way, right? Okay, it is revolving around the center of the disk. So now in this case, what will happen, right? Suppose like this way it is revolving with the constant angular velocity omega. In this case, what is happening? Initially, suppose acceleration is not 0, but suppose at any moment, right, the tangential acceleration is acting on the particle. It means that omega is getting changed. Either it is getting increased or it is getting decreased depending on the direction, right, in what direction the acceleration is applied. So here in translatory motion, right? As because of some external force, the state of the object is getting changed. So this change, this object does not want. So as of that, one property is acting inside the object, that was inertia in translatory. Same here, the particle is performing the rotational motion, either it is at rest, first case, or suppose it is performing the rotational motion, right? It is on moving on the disk, right, with respect to the center with a constant angular velocity omega. Now suppose if tangential acceleration is acting, some external force is acting tangentially to that, and at that moment, if suppose, right, the state of the object is getting changed. So in rotational motion, that resistance to the change is moment of inertia. That resistance to the change is what? Moment of inertia, right? So it's completely depends on the external force. See, if I'm talking about the translatory motion, right, and I'm talking about the rotational motion, see, I'm showing you all, right, the proof of that. See, in a translational motion, force is equal to m and a. So acceleration is inversely proportional to, right, acceleration is inversely proportional to mass, right? Okay, acceleration is inversely proportional to, right, mass. Similarly, right, the rotational analog of the force is torque. Torque, that is equal to I alpha, right? So here the alpha is an angular acceleration, that is torque by I. So alpha is inversely proportional to moment of inertia. You can see this equation here. In translatory motion, right, okay, acceleration is the maximum amount of the acceleration that is increasing. It doesn't mean mass is decreasing, right? Mass is trying to resist that change, and that is a property. Same here, if the alpha is increasing, or it is the state of the object is getting changed here, right, okay, the property of the object is trying to resist. So one, that is happening into the translatory motion, second, that is happening into the rotation, right? So that what's the inertia is, right? Okay, so now that's the moment of inertia. Now what actual the moment of inertia is, and what's the radius of the gyration? Okay, see, moment of inertia, first of all I want to define that state, right? Okay, the quantitative measure of inertia in the rotational motion. If I want to define MOI, the moment of inertia, right, MOI stands for moment of inertia, the quantitative measure of inertia in rotational motion of a body it is defined as the MOI, moment of inertia. Let us take another example. Suppose this is a disk, this is the center of the disk, and this is an axis of the rotation, right? Now let us take an example. Suppose if mass m is attached at the edge of the disk, right? Mass m is attached at the edge of the disk. Now it is rotating with the constant angular velocity omega, right? Okay, now what will be the value of the inertia? Right, the formula of the inertia is I, that is equal to, actually the formula is mk square, right, where k is the radius of gyration, right, radius of gyration, right? But generally this radius of gyration, right, okay, it is, right, the value of the k is right, changing with respect to the rigid bodies, right? Okay, the k value, right, changes, right, with respect to the rigid bodies, right? Okay, so for, right, to understand it right easily, right, we use the formula of the moment of inertia. Generally for the particle it is mr square, right? For a particle it is mr square. Generally we are taking it as a, for a particle, if I'm talking about, right, if it has a distance r, it is mr square, where r is a distance between particle, it is a distance between particle, right, and axis of rotation, right? If it is a rigid body, then moment of inertia is equal to, it's dm r square. We need to use this formula, right, for the rigid bodies to calculate the moment of inertia. Right now, see, moment of inertia completely depends on the radius of the gyration. The more amount of the value of the radius of the gyration, the more amount of the inertia we are having. Right. See, two most important stuff. Right. Okay. See, here I am writing. First, nearer to axis of rotation, less inertia, or you can say minimum inertia. Right, minimum, right, moment of inertia. Okay, far away from AOR, that is axis of rotation, right, more moment of inertia. Right. Okay, so moment of inertia completely depends on only two things: how mass is distributed, right, okay, about axis of rotation. It completely depends on the two things. First thing, that how mass is distributed, right, and how mass is distributed about axis of rotation. If axis of rotation is getting changed, the value of the inertia is getting changed, right? If the mass distribution is getting changed, right, the value of the inertia is getting changed. See, it's a very simple, right? According to the formula, I is equal to mk square. We are having in two physical quantities, right? If the densities are getting changed, mass uniform, see, we have used this term, na, uniform mass distribution, non-uniform mass distribution, right? This kind of thing. If it is a uniform mass distribution, it's okay. Moment of inertia depends on two things, right? How mass is distributed and how axis of rotation is situated, right? Axis of rotation is getting changed or displaced, inertia will get changed, right? Mass, suppose a mass is not uniformly distributed along the surface, or it is not uniformly spreaded along the surface, obviously the inertia is going to change, right? So the moment of inertia is having the very simple, okay, on this questions, right, the MC, on this 2 points, right, the MCQs are asked, right? On this 2 points, the MCQs are asked into the examination, right? So I'm moving aside. If you want to have a snap of it, right, on the countdown of 5, 4, 3, 2, 1. So for particle, it is mr square. For rigid bodies, we are having the formulas that you all are completely aware of, right? If it is a rod, right, okay, suppose if you want to move on to the derivation of rod, then it's not a big deal, I can show you, right? Suppose it is a rod, this is a rod, right, okay, I have taken the dm mass, right, at the distance of x square, sorry, at the distance of x with respect to this is my axis of rotation, right? Suppose I am taking I, that is equal to integration of dm, that is equal to x square. Mass is uniformly distributed, so lambda is equal to mass per unit length, and that is equal to dm by dx, right? So here I am getting dm, that is equal to mass per unit length into dx. Replacing here, I am getting moment of inertia as mass per unit length into dx into x square, right? Okay. Now, limits will completely depend on between 2 points, right? You want to calculate the inertia. So if I'm calculating this, I'm getting ml square by 3 as a moment of inertia, right? Suppose if you want to calculate the moment of inertia, right, okay, for a rod where axis of the rotation is lies in between. See, first axis of rotation was this, now axis of rotation is it, right? So it means inertia is getting changed, right? Same thing will happen, right? But right, we are only going to have the change in limits, right? Okay, the limits will be, right, I'm sorry, it will be not dx square, okay, it will be equivalent to dx, right? Limits will be minus L by 2 to plus L by 2. This will be minus L by 2 because now this is axis of rotation, so that will be the reference point, and reference point we need to calculate it as a 0. We need to take it as a 0. So here we will get it as moment of inertia as ml square by 12. So like this way, right, if axis of rotation is getting changed, things are getting changed, right? Okay. So now, okay, these are the formulas, right? Okay, if it is a right, any rigid body or a particle, you can take it as mr square. Nearer to the axis of rotation, minimum value of the inertia is 0. Far away from the axis of the rotation, it is mr square, right? Suppose if it is a rigid body also, then we can consider, right? It completely depends on what kind of the application it is mentioned. Right now, this thing, right, for a disk mr square by 2, right, for a hollow sphere, right, okay, for a solid sphere, hollow sphere we are having 2 by 3 mr square, for solid sphere we are having 2 by 5 mr square, for a rod in between we are having ml square by 12, from the edge it is ml square by 33, right? So this all formulas are all there, right, for the moment of inertia. Now in this moment of inertia we are having the two type of the theorems, right? Okay, we can calculate the moment of inertia for the multiple rigid bodies, right? And for this, yeah, direct sums are getting asked, right? Okay, now let's see what actually the perpendicular axis theorem states. See, perpendicular axis theorem states that, first of all, the most noteworthy, the most important point regarding it, the perpendicular axis theorem is only applicable for 2D objects, 2D laminas, only applicable. It is not applicable to the 3D objects, that is having the length, breadth and width kind of things. Length, breadth and width, right? Okay, length, breadth and height kind of things, dimensions, right? The perpendicular axis theorem only exists for, right? Only exists for. Now, while dealing with the perpendicular axis theorem or parallel axis theorem, some of the things you need to take on into the mind. We are having two axes of rotation. Always keep this into the mind. The first one is an axis of rotation about which inertia is known. Axis of rotation about which inertia is known, like I've shown you all into the formulas. Second, DAOR, that is desired axis of rotation. Desired axis of rotation about which we need to calculate moment of inertia. So basically, while solving the sums of moment of inertia, we are going to deal with the two types of rotations. Sorry, two types of axis of rotations. First one, about which we are aware what actually the value of inertia, the moment of inertia is. Second, desired axis of rotation about which we need to calculate the moment of inertia. This is always given, this is asked. Suppose AOR, the given axis of rotation is perpendicular to DAOR, the desired axis of rotation, then we are going to use the perpendicular axis theorem. First point. Second, if axis of rotation is parallel to desired axis of rotation, then we are going to use parallel axis theorem, a very simple stuff. Two axes of rotation, one about which, right, we know the value of the inertia, second, right, about which we need to calculate the value of the inertia, right? So data given, data needed. Data given, axis of rotation, data needed, axis of rotation. If data given and data needed axis of rotation are perpendicular to each other, obviously we are going to apply perpendicular axis theorem. If they both are parallel, then we are going to apply the parallel axis theorem. Perpendicular axis theorem is only applicable for the 2D laminas, right? So this thing is quite important, right? Okay, you can have a snap of it. This is quite important, right, to solve the sums of the moment of inertia. Now let's see, right, how we can move on to the perpendicular axis theorem. Suppose this is a disk, right? This is the axis about which, right, it is getting rotated. One is a disk, right? Can I draw, right? See, this is x-axis, this is y-axis, and this is a third one, z-axis, right? This is the axis of rotation about which moment of inertia value is known, as I told you all, okay, few moments, right, okay, before, okay. This is a z-axis, right, we are aware of, we have seen into the formula. This is a disk, right, for an axis of rotation that is passing through the center of mass and perpendicular to the plane, we are having the moment of inertia as mr square by 2. Now we need to calculate the value of moment of inertia about the axis that is passing through, right, x and y. So this is our desired axis of rotation about which we needed to calculate the moment of inertia. This is the known axis of rotation about which we are having the value of inertia mr square by 2. In this case, we are using the perpendicular axis theorem. Suppose this is a mass dm, it is rotating along the circle, right? So can I say this distance as y, this distance as x, right, and this distance as, right, under root of x square plus y square. I have taken the, right, an object of mass dm, right? I have taken the object of mass dm, right? Okay. Now see, it's a very simple thing. About x-axis and about y, mass is equally distributed in all directions. About x-axis of rotation and, right, y-axis of rotation, right, mass is equally distributed in both. It means one thing is same, the moment of inertia about the x that is equivalent to going to be same as moment of inertia about the y. Equation number 1. Why this is happening? Because around x and y, in both of the cases, the mass is equally distributed. See, suppose along y, if you are talking about, see, mirror image is formed. Suppose along the x you are talking about, mirror image is formed, right? Along y, along x, right, in both of the cases, right, the mirror images are formed. It means mass is uniformly distributed about that axis of rotation. Right, about that axis of rotation. So it means moment of inertia around the both are going to be equal, right? Okay, so can I say the resultant moment of inertia as under root of x square plus y square? See, r square, can I say according to the Pythagoras theorem, that is equal to x square plus y square, right? For a mass dm, can I multiply here dm? Can I multiply here dm? So I'm getting dmr square, that is equal to dmx square plus dmy square, right? Now see, suppose I'm talking about this mass dm, right, this mass dm. If I'm talking about the x-axis, right, okay, then this would be the distance x, right? Sorry, about y, this is y, right, and this is x, and this is r, right, and this is what the axis of rotation of the disk is, right? So can I say this is a moment of inertia along the z-axis, this is a moment of inertia along y-axis, this is a moment of inertia along x and y. So this is a proof of the perpendicular axis theorem, right? Just a simple proof using the Pythagoras theorem, right? A simple proof using the Pythagoras theorem. Now using this equation we are going to calculate. See, we got this is the equation of the perpendicular axis theorem, right? If z is an axis of rotation, then this will be ix plus iy, right? If you are writing it as iy, then it will be iz plus ix depending on an application, and if you are writing it as ix, then it is iy plus iz, right? It completely depending on application, right? So these are the three important formulas for the perpendicular axis theorem, right? Okay, and this is the proof using the Pythagoras theorem we obtained that. Okay. Now suppose, let's take an example. This is the disk, right? Two axes of rotations, one about which we are known to the value of inertia, second about which we needed to calculate the value of inertia. So this is the known axis of rotation, right? And this is my desired axis of rotation about which I need to calculate the value of inertia. About this I am known. If it is a disk, then it is mr square by 2, right? Students always used to get confused where you need to apply the perpendicular axis theorem or where you need to apply the parallel axis theorem. So in this case, guys, that's why I had classified the known axis of rotation, the desired axis of. If known and desired, they are perpendicular, obviously we need to apply the perpendicular axis theorem. If known and desired are parallel, yes, we need to apply the parallel axis theorem. So here they both are perpendicular to each other, right? Okay. So it means that on applying, right, perpendicular axis theorem, and it is only applicable, as I said, right, on the, okay, 2D objects, perpendicular axis theorem, right? So how I'm going to get this stuff, right? Okay, I on known axis of rotation is equal to I on y plus I on x. Now, as I said, as mass distribution along x and y is equal, so these two things are going to same. So 2I along the x, that is equal to I, known axis of rotation. So I along the x, that is equal to mr square by 4. So this is the moment of inertia, right? Okay, along the desired axis of rotation, right? Desired axis of rotation. This is how, right, the parallel axis theorem, the perpendicular axis theorem is applied, right? Individually, we are not going to see the sums individually, but right, we are going to calculate the lots of, we are going to see that stuff, but in that, right, there will be the combined use of perpendicular and parallel axis theorems. Now what does the parallel axis theorem say? It's simple. Known axis of rotation, desired axis of rotation. If both are perpendicular, we need to apply the perpendicular axis theorem, and suppose if they both are parallel to each other, we need to apply the parallel axis theorem. Again, I'm going to take the same example. This is a disk, right? Okay, it is rotating with respect to the center of mass, right? It is rotating with respect to the center of mass. So this is obviously my known axis of rotation, right? This is obviously, right, my known axis of rotation, right, about which I am aware of. So the moment of inertia value is mr square by 2. What will be my desired axis of rotation? At the distance x. See, they both are parallel. This is an desired axis of rotation, right? The known axis of rotation, right, it is parallel, right, to desired axis of rotation, right? So in this case, right, we are going to use the perpendicular axis theorem, right? We are going to use what? The perpendicular axis theorem. Sorry, the parallel axis theorem, right? What it states? Suppose this is a known axis of rotation k nor, right? And this is a desired axis of rotation. The distance between them is x. So according to the parallel axis theorem, according to parallel axis theorem, so this is known axis of rotation that is equivalent to what, right? Okay, I'm sorry. Okay, I is desired axis of rotation, that is equal to, right, known axis of rotation plus m of the object into x square, where x is distance between known axis of rotation to desired axis of rotation, right? Known axis of rotation to desired axis of rotation, right? So this is what the formula of the perpendicular axis, parallel axis theorem is. It is applicable for all objects, all rigid bodies, 2D, 3D, right? It is not having any kind of the limitation, right? Okay, the perpendicular axis theorem is having the limitation. The parallel axis theorem is, right, we can apply it anywhere, right? Okay, now let's say an example for it. Suppose the same disk we took, right, about the axis of rotation that is passing through center of mass. We are aware of what actually the moment of inertia is. Using the perpendicular axis theorem, we calculated, right, the value of the moment of inertia about this axis of rotation is mr square by 4. Now this is my known axis of rotation. What will be my desired axis of rotation? That is passing through r by 2 and parallel to it. It's very simple. I desired axis of rotation is equal to I known axis of rotation plus mx square. X here, the value between the two axes of rotation is r by 2, right? So the desired axis of rotation about known, we are having mr square by 4 plus mr square by 4, right? Because x value is r by 2, so here square by 2. This is the value of the moment of inertia about the desired axis of rotation, right? Value of the moment of inertia. So about this axis we are having mr square by 2, right? So the axis of rotation is getting changed, the value of the moment of inertia will get changed, right? If the mass distribution about axis of rotation is getting changed, the value of the inertia will get changed, right? If the mass if the mass value, mass distribution along the if the mass distribution, right, around the axis of rotation is getting changed, right, inertia is getting changed. If if there is a like change into the axis of rotation position, right, okay, then the value of the inertia is getting. So this is all what about the moment of inertia is. Okay, now see, there are some right concepts of moment of inertia for the combined bodies, right, and there are some moment of inertia for the cavities, right? First of all, let's move on to some basic sums of the moment of inertia. Slowly we are going to increase the complexity level, right? Slowly we are going to increase the complexity level. Okay, now first of all, the first question that has been asked in NEET Phase 2 2016. A light rod of length L has two masses, m1, m2. Attached to it two ends. The moment of inertia of the system. See, rod is light. This is mass m1. This is mass m2. They are connected to the light rod. It means that's very simple thing, right? We need to avoid the mass of the rod. Moment of inertia of this system about an axis perpendicular to the rod and passing through the center of mass of the system. What will be the center of, see, first of all we need to calculate the center of mass. So center of mass, that is equal to m1 x1 plus m2 x2, right, whole divided by m1 plus m2. So if I am considering this as a reference point, right, then our center of mass will be m2 of L whole divided by m1 plus m2, right? This will be the center of mass of the system. This will be m2L whole divided by m1 plus m2, and this distance will be m1L whole divided by m1 plus m2. Right, now this is our desired axis of rotation about which we needed to calculate the value of the center of mass. if there are if in the entire system, if there are two objects, right, then value of the inertia is going to get submitted, right? Suppose here two objects are there, and then we are going to have I1 plus I2. If cavity is removed from the object, then we are going to have total minus cavity that has been removed, right? So now I, what is mass 1? See, can I say R1 square M2 R2 square? Because they are the particle. This is our axis of the rotation. This will be the R1 and this will be the value of R2. R1 and R2 are the radiuses, right? What will be the value of R1? I, that is M1. R1 will be M2 square L square whole divided by M1 plus M2 square. What will be the value of R2? M2 M1 square L square whole divided by M1 plus M2, right, square, right? So in this, right, I will be M1 M2 L square, right? It is M1 plus M2 whole divided by M1 plus M2, right, whole square. So one thing is gonna cancel. So final the moment of inertia is M1 M2 L square whole divided by M1 plus M2, right? So this is a moment of inertia about the system, of a system, about an axis that is perpendicular. See, this is perpendicular to the rod and passing through the center of mass, right? The first will be the perfect answer. You can see, right? I'm moving aside, right? You can see this stuff. Come on, everyone, right? I'm moving aside. You can see this stuff. Now, let's move on to the next part. See now, combined bodies. 2015, cancelled exam. 3 identical spherical shell, each of mass m. See, they are spherical shells. 3. This is our desired axis of rotation, right? This is our known axis of rotation about which we are going to have, right? We are aware of what actually the value of inertia is. So 3 objects are there. The moment of inertia of the system, that will be equivalent to I1 plus I2 plus I of 3. I1, I2 and I of 3. Right now, see, okay, I'm going to solve it here only. Okay, can I consider this is 1, this is 2 and this is 3? Okay, now here we need to apply the parallel axis theorem. See, if I'm talking about the first, our desired axis of rotation and known axis of rotation, they both are overlapping each other, right? This is our known axis of rotation and this is also our desired axis of rotation, and it is a spherical shell, the 3D object. So I1 value will be 2 by 3 mr square. That is the value of the moment of inertia of the shell about the center of mass of the system, right? We have seen this into the formula. See, 2 by 3. You can see this stuff, right? It is 2 by 3, right? Shell. It is passing through the center of mass, na? Right? Now, the same thing. Let's see this. So for first, we got the value of the inertia as, right, 2 by 3. Now for second, about this axis of rotation, we are known to the value, but our desired axis of rotation is at some distance away from our known axis of rotation, and it is parallel. Desired axis of rotation, it is somewhat far away, distance far away from the known axis of rotation, and they both are parallel. It means immediately it should get clicked in your mind that yes, we need to apply the parallel axis theorem. For second, known axis of rotation 2 by 3 mr square plus mass of the object. How much distance this is? R. The same thing is going to happen for third. It's 2 by 3 mr square plus mr square, right? If you're solving this, you are getting the final moment of inertia of this system about the desired axis of rotation as 4 mr square. B is the perfect answer for this specific question, right? Generally the moment of inertia for the combined bodies is only asked, right? The moment of inertia of a disk of mass m and radius r. See, there is one disk, mass m is given, radius r is given, which is tangential to the circumference of the disk and parallel to the diameter. They are going to stuck you in this kind of the grammatical things, right? Tangential to the circumference and parallel to the diameter. Suppose this is a diametric axis we are taking. Tangential to the circumference, can I say this is our desired axis of rotation about which we need to calculate the value of moment of inertia? Is it tangential to the surface circumference? Yes. Is it parallel to this? Yes. This is our known axis of rotation. Are they both parallel? Yes. Which theorem we need to apply? Parallel axis theorem, right? So I of desired axis of rotation, I of known axis of rotation plus m, mass of the object, into distance r square. So known axis of rotation, as it is a disk, this thing we have already calculated. About this we are having mr square by 4 plus mr square, right? So we are having 5 by 4 mr square, right? This is a moment of inertia about the desired axis of rotation, right? Moment of inertia about the desired axis of rotation. The first one is a perfect answer. The ratio of the radius of gyration. See, now radius of gyration is something else, right? The ratio of the radius of gyration. See, actually the moment of inertia value is, right, mk square, where k is the value of the radius of gyration. K is the value of the radius of gyration, right? Now suppose if I am writing for a disk, right, it is mr square by 2. If I am comparing this to mk square, then value of the radius of gyration is r by root 2. This is how things are evaluated, right? This is how, right, the things are evaluated. Now, the ratio of the radius of gyration of the circular disk about tangential axis in plane, okay, perpendicular to the plane and, okay, this is a disk, right? We need to calculate the ratio first. Second, right, one that is passing through the circumference but that is perpendicular to the plane. Second, that is passing through the circumference tangentially, right, to the circumference but is in the plane. So this is perpendicular to the plane, this is in the plane. About this we have already calculated 5 by 4 mr square, right? About this, I'm sorry, we have already calculated, right? In the previous question we have already calculated. About this we are having 5 by 4 mr square, right? Moment of inertia about this, right? And about this, right, it will be from here, it is mr square by 2, and from here we are going to have 3 by 2 mr square, right? So can I consider this as 1 and consider this as 2, right? So I1, that is equal to 5 by 4 mr square. Can I consider it as mk1? So what will be the value of K1? Right, that will be under root of 5 by 2. Right, similarly value of K2, that will be under root of 3 by under root of 2. Right, so this is the value of the K1 and this is the value of K2. Right, okay, so if we are taking, this is the final step, if we are taking, right, I1 by I2, that is equal to K1 by K2. Right, I1 by I2, that is equivalent to K1 by K2. Right, okay, so we are having root 5 by 2 into root 3 into root 2. So I1 by I2 ratio, that will be equivalent to root 5 by root 6. Right, and that is equal to radius of gyration ratio. Okay, right, C is the perfect answer. We are going to see some more examples of the moment of inertia. Right, we are going to see the more examples of the combined bodies, of the cavities, right, lots of the things, right, we are going to discuss just into the few minutes. The one of the most of the important results, right, that we are going to discuss. Suppose if this is an axis of rotation, right, and the rod is placed like this way and this is a theta, right, and how to calculate the moment of inertia. See, there is a derivation behind it, but I'm going to show you all the direct formula related to it. Right, suppose this is a theta, right, theta should be right between the rod and vertical, between the rod and the vertical, theta should be between the rod and the vertical. Okay, now let's move on to the next part. See, what will be the formula of this, right? So formula will be ml square by 3, right, it's sine square theta, ml square by 3, and that is equivalent to sine square theta, because always, right, if the object is tilted at the some angle, right, and right, always the perpendicular is dropped. Suppose if we are drawing a perpendicular, right, and plotting up the distance, right, suppose if we are drawing a perpendicular like this way, right, and plotting up the distance, then we are having the same as L. Suppose this is a theta, then what will be the perpendicular distance? It will be L sine theta. Right, okay, there is a complete derivation behind it. We are not moving on to that part right now. Suppose this is the first case. Now suppose if I'm talking about the second case, right, if the rod is like this way, right, okay, an object is kept like this way, and this is the theta, right, then moment of inertia will be I is equal to ml square by 12, right, sine square theta. So these are the two most important formulas. Okay, now let's move on to the next part. Suppose this is a disk of the radius r, another disk of radius r by 2 is kept. What is the moment of inertia about the system? Right, this is our desired axis of rotation. Say in center of mass we calculated, again the masses are not given, right, the masses are not given, the dimensions are given. So using the density, sigma is equal to mass per unit area, right, okay, I'm going to first of all calculate the mass of the larger disk, that is equal to density into pi r square, and mass of the smaller disk, right, that is equal to density into pi r square by 4. So that is mass of larger by 4, right, mass of larger by 4, right. Now what will be the moment of inertia of the combined object? I is equal to, right, I1 plus I2. So that will be is equal to mr square by 2. See, this is all about the formula. For the larger disk, right, about the axis of rotation that is passing through its center of mass, right, it is mr square by 2. For a smaller disk, formula is mr square by 2, but mass is m by 4, radius is r by 2, and this 2 is of formula. So moment of inertia is mr square by 2 plus mr square whole divided by 32, right. So the resultant moment of inertia is 17 by 32 mr square. right? Sums are quite easy, but students always used to get confused and get stuck into the calculation parts, right? Here, see, we are having very less amount of the time and that kind of the exam environment we are facing, right? So here, actually, we are aware of this formula. Actually, it is mr square by 2. But we used to forget to replace this values of m by 4, r as r by 2, right? Like all of those stuff, like all of those calculation mistakes are going on always, right? Like all of those calculation mistakes are going on always. Okay, so now let's move on to the next sum, right? Okay, now moment of inertia for the cavities. How to solve this kind of the sums? Again, I'm taking one example of a disk, right? This is an axis of rotation. Now the radius of the disk is r. Suppose if I am removing the cavity of r by 2, right, of the radius r by 2 from the disk. This much part is removed. So what will be the moment of inertia of the remaining system? What will be the moment of inertia, right, of the remaining system about the axis of rotation passing through? This is our desired axis of rotation. Now, cavity is removed. In combined bodies, right, if we are having more than one, then we are going to add the inertia. If, right, the cavities are right there in the system and the things are removed, then we need to subtract. So moment of inertia of the remaining, that is moment of inertia of whole system about desired axis of rotation minus moment of inertia of cavity about desired axis of rotation. Whole system about this axis minus cavity about this axis. Why we selected this axis? Because in the question it is mentioned that we need to calculate the moment of inertia for the remaining system about this desired axis of rotation. About this desired axis of rotation, right? Okay, so now let's move on to this part. Okay, now, so what will be the moment of inertia for the remaining system? See, masses are not given. So density is equal to mass per unit area. For mass of whole disk, right, that will be is equal to pi r square into sigma, while mass of cavity, that will be is equal to, right, m by 4. I think we have calculated thousands of times, right? So now remaining system, the moment of inertia of the whole system about this axis minus. Now if I'm talking about the cavity is also a disk, so moment of inertia about this is m by 4 r square by 4 into 2. Actual formula is mr square by 2, but mass is m by 4, radius is r by 2, so we are getting this. But we need to calculate the moment of inertia of this disk about this axis, so we need to apply the parallel axis theorem, right? So it will be mr square by 4 into 4 into 2 plus parallel axis theorem. What is the mass? M by 4. What is the distance? R by 2, and that is r square by 4. So we are getting the moment of inertia of the remaining system as mr square by 2 minus mr square by 32 plus, right, mr square by 16, right? Okay, I think let me just check it out. Okay, 16 plus 1, 17. Okay, same here, but this time I think 16 is there, so it will be IR, this is mr square by 2 minus 16 into 2, we are going to take the LCM for this, so 2, it's minus 3 mr square by 32, right? So the moment of inertia of the remaining system about desired axis of rotation, right, that is equal to 13 mr square by 32, and that is the perfect answer for this specific question, right? So this is how the moment of inertia of the cavities are being calculated, right? Okay, So now let's move on to the next concept, right? That is torque. So students, till now we have seen to the concepts of the moment of inertia, the center of mass, all of the stuff we saw. Now let's move on to the most important, the dynamics part, right, in which we are going to see the torque and conservation of angular momentum. See, angular momentum and its relevant directions you all are aware of. So, but a maximum number of the questions they had been, the most expected part is from conservation of angular momentum, right? So we are going to see, right, what kind of the questions they are asking from torque, right, and what kind of the question they are asking from the conservation of angular momentum. Now let's see. See, before moving on to the dynamics part, right, we need to move on with some of the important variables, right? See, it's a very simple difference that I want to show you all in front. If I'm talking about the rotational part, right, and if I'm talking about the translational part, if I'm talking about the rotational part, and if I'm talking about the translational part, right? Translational motion. In translational motion, we are having displacement, right? We are defining it as an S. We are having the linear velocity of a particle. We are defining it as a V. We are having the linear acceleration of the particle, right? We are defining it as an A. We are having a momentum of the particle, right? We are defining it as a P. We are defining, right, the force of the particle as F. Relevant to this linear variables, we are having the angular variables. Linear variables are for the translational motion, while the angular variables are for the rotational motion. All of those angular variables, there is one important note regarding all of this angular variables, they always lies on the axis of rotation, right? They are basically two kind of vectors are there, polar vectors and axial vectors, right? Axial vectors are those that lies on the axis of rotation, and spatially for, right, they are for the rotational motion, right? So maximum, if I'm talking about the rotational motion vectors, right, these angular variables, they all lies on the, right, axis of rotation. So for displacement, against the displacement, right, analogy to that, we are having the angular displacement, right, and that we are, the notion is theta. Against to the velocity, we are having the angular velocity for the rotational motion, right, and we are defining it as an omega. Against to acceleration, we are having the angular acceleration, right, and we are defining it as an alpha. Against to momentum, we are having the angular momentum, right, so we are defining it as an L, right, and against to force, we are having torque. That's why the torque is defined as the rotational analog of the force, right? The rotational analog of the force, right? So these are some linear variables, right? And on the opposite to that, there are some angular variables. There are some linear variables, and opposite to that, there are some angular variables, right? Now, there are some relation between them. Suppose if you want to calculate the S, then it is always R into theta, right? If you want to write down V, then it is always R into omega. If you write down the relation of the acceleration, that is always R into alpha. If you want to write down the relation of the momentum, right, so this angular momentum is always Rp, right, or Rmv, right, and if you want to calculate the torque, that is Rf, right? This all are of the magnitude I'm talking about. So this is all are the relations between the linear variables and angular variables, right? This is a linear variable, this is a list of the this is a list of the linear, this is for the angular, and this is the relation between them, right? So in dynamics, I think we are going to maximum deal with this kind of the quantities, right? And rest of the thing, I think they're going to come in front and you will be aware of it. So after center of mass, after moment of inertia, yes, now we are going to deal with the torque. Rotational analog of force, right? If I want to define torque, right, simple rotational analog of force. Force, it is going to increase the linear acceleration of the object, or see, whenever the acceleration is applied on that object, obviously the velocity is going to increase or decrease. Again, I'm going to take one example. So it's very simple thing, right? Suppose this is an object, right? It is of mass m, right? Initial velocity is 0. Suppose acceleration is applied, velocity obviously either it is going to increase or it is going to decrease. Suppose it is going to increase because acceleration and velocity, they both are in the same direction. It means whatever the forces applies to the object, it is, right, increasing the velocity of the particle. Now this is for translational motion. Now same happens for the rotational, right? Same happens for the rotational. Let us take an example, right? The disk initially at rest, initial angular velocity is 0. Disk initially at rest, the initial angular velocity is 0. Now suppose suddenly a tangential force starts acting into the object and this velocity is getting increased to omega, right? It is going to increase, right, to omega. So it means if this tangential force, right, is producing a torque, it is producing a torque that changes omega. It produces a torque that changes the omega, right? Okay, so here the omega is getting changed. Here force was responsible to change the velocity of the particle. Here the tangential force is responsible to change the angular velocity of the particle. So here the torque is produced. That's why it is the rotational analog of the force. Examples of the torque. You can see spanner, torque, torque, torque. This is torque. This is torque. This is torque. Right? So that's right, the most important thing, the torque. Okay, the rotational analog of the force, the formula of the torque, that is always R cross F, the cross product of R cross F, or RF sine of theta, right, and unit vector n. Okay, now in this case, right guys, this is an actual formula of the torque, right? And if you want right, torque to be maximum, generally this is also we are using, then it is always RF into unit vector n, right, into unit vector n. Then this is the case in which the torque is always maximum, right? You all are aware of the torque, right? Okay, now let's move on to the most important part, the equilibrium conditions of the, right, that we are going, the most two important things we are going to use right now. First, the equilibrium condition, and second, the conservation of the energy. First, the equilibrium condition, and second, the conservation of energy, right? Okay, so this is nothing else but the actual formula of the torque. How we are going to use this, how we are going to calculate it, right? Okay, you have to just keep one thing into the mind, right? The concepts of the cross product of the vectors, right? Okay, cross product of vectors will be maximum used in solving the sums of rotational or the dynamics. Cross product of the vectors will be maximum used. Equilibrium conditions. Basically, we are having the, right, some of the equilibrium conditions we have seen into the NLM. What were those? Right, suppose the net acceleration along the x direction is 0, right, then all the forces, the summation of all forces acceleration will be 0. If the summation, the net acceleration along the y is 0, then summation of the all y forces will be 0. If net acceleration along the x direction is not equivalent to 0, then summation of the all forces will be ma, right, net acceleration along the x direction. And suppose if net acceleration along the y direction is not equivalent to 0, then summation of that is ma into net into y direction, right? summation of the all forces is not equivalent to. So this were the conditions of the translational motion. So that's why they are known as, right, the translational equilibrium conditions, right? Translational equilibrium conditions, right? Translational equilibrium conditions, right? Okay, now let's move forward to the next part, right? Translational equilibrium condition. Okay, now let's move forward to the next part. What are the conditions for the rotational equilibrium? If net torque about center of mass is 0. Basically, torque are of two types. First, clockwise torque. Second, anti-clockwise torque. Right? Okay. In which direction torque is getting produced, we are going to see all of those things into the sum. If the net torque is 0, right? Two conditions are there. Then we can say the system is in equilibrium. System is in rotational equilibrium. System is in rotational equilibrium. And this means that all the summations of the torques into the anti-clockwise, that is equal to all the summations of the torques, they are in clockwise. Right? If the net torque about the center of mass is 0 or any specific point. If this is not happening, this is not happening. Suppose the net torque around the center of mass is not equivalent to 0. It means that not torque, right, about any specific point, that is always equivalent to I alpha. Right? So these are the conditions for the rotational equilibrium. So these are the rotational equilibrium conditions, right? Rotational equilibrium conditions. Right? Rotational equilibrium conditions. We are going to use this stuff maximum in this chapter, right? And the concepts of torque. First of all, we are going to see the torque into the very basic manner, and then right, we are going to into the right roots, and we are going to increase the complexity level of the sums. Now, first of all, a very simple thing: how to calculate a torque. See, find the torque about the origin when force. See, this question, this simple question related to the torque has been asked in NEET 2020. Force that is equal to R cross F, right? Force is 3J Newton. Position of the particle vector is 2K, right? Force is 3J, right? Force is 3J Newton, and the position vector of the particle is what? 2K. What will be the value of the, right, torque? What will be the value of the torque? Right? Yes, this is an exact symbol. Now, okay. See, suppose if you want to calculate, we can say the cross product of R and F is torque. So whenever you want to calculate the cross product, right, it is always done by means of determinant. A small mathematics is there behind it, right? A small mathematics is there. Using the determinant, suppose if in this case, if I want to calculate the force, then this torque, that will be, this is I, this is J, and this is K. First of all, in this line, always R components are kept, and then F components are kept. Here R is on only Z direction, so can I say this is 0, 0? Here F is in only J direction, right? So can I say this is 3, 0, 0? So if we are calculating the torque, right? Now how to solve this determinant, right? In this, right, we are going to solve this into the very, I'm going to solve this, but in the next sum, right, I will show you all into the detail how the determinants are resolved, how they are converted into the 2 cross 2 determinants, right? Right, these are 3 cross 3 determinants, 3 rows, 3 columns, right? 3 rows, 3 columns. Okay, here the answer will be negative of 6 of I. Torque will be negative of 6 of I Newton meter. But how we reach up to here, I'm going to show you all. But this question has been asked in NEET 2020. Okay, now let's see this. Suppose R is 1, 2, 3 and F is 2, 1, 1. Position vector is given, force vector is given, and we need to calculate the torque. Position vector is given, force vector is given, and we need to calculate the torque. See, it is done by means of determinant. This is 3 cross 3 determinant. 3 cross 3 determinant, it means that 3 rows and 3 columns. I, in first, we are writing it as I, J, and K. And then immediately components of the R are kept. And then components of F. See, in determinants, we are not having the direct solutions for 3 cross 3. In some of the cases, even we are having the sums. Those who are students of mathematics, they are even aware of the right concepts of 4 cross 4 determinants. We are not having direct solutions for this. We are having only direct solution for 2 cross 2 determinants, in which we are having 2 rows and 2 columns. So what happens here? If 4 cross 4 and 3 cross 3 determinants are asked, then first there is a technique, right? There is a way to convert them, to transform them into the 2 cross 2 determinants, and then they are resolved. So suppose if this are 3 cross 3 determinants, then first we need to transform this stuff in 2 cross 2. Now how we are going to do that? Suppose if I am picking this I, this will be 2 cross 2, right? Forget this row and forget this column. Forget this row and column and write the remaining stuff. Whenever you are dealing with J, always keep it as a negative, right? Okay, now forget this row and column. Just write down 1, 2, 3 and 1 plus K. So this all will be 2 cross 2 determinants. This all will be 2 cross 2. Now suppose if you are moving on to K, remain like forget this row and column, then we are having 1, 2, 2, 1. So successfully we have converted, right, 3 cross 3 determinants to 2 cross 2. We have converted 3 cross 3 determinants to 2 cross 2. Now we are having solution for this. Talk. Suppose if I am talking about I, we need to cross multiply. That will be 2 into 1 minus 3 into 1. Minus J, right? 1 into 1 minus 3 into 2, 1 minus 6. Plus K, 1 into 1 minus 2 into 2, 4. So value of the torque, it will be 2 minus 3, that is minus of I, minus 5 of J, minus 3 of K. This is the value of the torque that is acting on a position, right, when this force is applied. So whenever there is a particle on this position and this much amount of the force is applied, it means that, right, this much amount of the torque is acting on the particle. This is the general way to determine the torque, right, by the method of determinants. And why we use that determinant? Because torque is nothing else but a cross product of R and F, right? R and F of R, the two vectors, and the cross product of that, it is nothing else but a torque. Now this was the basic explanation. Now how, right, okay, the conditions of the rotational and see the this equations, how these conditions we are going to solve the sums into the mechanics. This is a quite important part, right? See now how we are going to use this torque. See, a rod, see this question is asked in NEET 2013. A rod PQ of mass M and length L is hinged at the end P. The rod is kept horizontal by massless string tied to the point Q. At this point it is hinged when the string is cut. Now suddenly the string is cut. Angular acceleration of the rod at just a moment when string is cut. Right? Just a moment when string is cut. See, rod is hinged about point P and it is tied with the string. System is in equilibrium, all forces are balanced, right? Everything is going on. Right? System is in equilibrium, all forces are balanced, and it's a good thing. Now, what will happen here? Suppose if string is going to be cut, then about this point P, this rod is going to rotate like this way. Suppose this is a point P, I'm cutting the string. So the rod will rotate like this way. Right? We felt that rotational part, na, torque is produced. We felt that rotational part, na, right? System was like this. This is a point P about which it was hinged. This is what the point about it was tied. String is cut, right? We felt a motion, we analyzed it, yes. The rotational was included, it means there is a torque. So after string is cut, can I say after string is cut, the net torque along the point P is not equivalent to 0. It means net torque along the point P that is equivalent to I alpha. If it would be equivalent to 0, then system would be in equilibrium. Either it could move into with the constant angular velocity, but no, right? Here the net torque about the point is not 0, right? Okay. Here the torque is produced, so it means that will be equivalent to our alpha. Now let's plot the FBT for this. See here. Now one thing we are confirmed that torque is produced, but who is responsible for that torque? Which force is responsible? See, right now we are having only two forces. One is Nx, this is Ny, this is a normal reaction, and the third one is Mg. This is the point about which we are going to calculate a torque. So it means torque produced by this normal components will be 0. Apart from this, when string was not cut, we were having tension, but now we are not having this force also, right? So it means that only Mg is responsible for producing a torque, and forces the object to move like this way. It forces an object to move like this way, right? So it means that this Mg, right, at the distance of L by 2, this is, see, always whenever you are calculating the torque, no, always take the perpendicular distance of the force. Never resolve the components of the force, always resolves the component of the distance, right? So in this, right, obviously you are going to take torque that is equal to, right, I of alpha Mg into L by 2. About the point P, the rod is rotating like this way. So what will be the value of moment of inertia? ml square by 3 alpha, right? So alpha, it will be equivalent to 3g by 2l. This will be the angular acceleration of the rod, right? C will be the perfect answer for this specific. Angular acceleration of the rod. Now, a rope is wound around the hollow cylinder of mass 3 kg and radius of 40 centimeter. There is one cylinder, right, like this way. Rope is wound around it. Mass of the cylinder, that is 3 kg. Radius of the cylinder, it is 40 centimeter. What is the angular acceleration of the cylinder if the rod is pulled up, right? See, suppose it is pulled up with the force of 30 Newton. This is mg, right? So what will be the angular acceleration? Now see, it is pulled up, na? So first of all, to calculate, to analyze, to come up to the result whether the net torque is acting or not, you have to check it out whether the object is getting rotated or not. So whenever the 30 Newton force is applied into the upward direction, cylinder is getting rolled and coming up. It means yes, torque is being produced. Right? Okay, this question has been asked into the NEET 2017. So can I say net, see, and that net torque is produced around the point O. It is not equivalent to 0 and we can say it is equivalent to I alpha. Right? Now, can I say what will be who is going to produce the torque? This force is going to produce the torque and this is the perpendicular distance R. So can I say 30 Newton into the perpendicular distance 0.4, that is equivalent to I of alpha. Right? Okay. Now, see. Alpha, that is equivalent to 30 into 0.4 whole divided by moment of inertia. Now what will be the moment of inertia, right, about moment of inertia of the cylinder, right, so that we can replace the value to get the value of the angular acceleration, right? Okay, to get the value of the angular acceleration, right? So I'm replacing this as 30 into 0.4 whole divided by, for a cylinder, right, can I write it as mr square, right? It is 3 into 0.4 whole square. So here alpha it will be 100 whole divided by 4, that is 25 radian per second square, right? So this is the angular acceleration of the rod. Yes, right, we got this stuff from the conditions of the rotational and translational equilibrium. This question has been asked in 2007 and 6 both. The uniform rod AB of length L and mass M is free to rotate. Initially the rod is just as kept like this way and it is released. If it is released, then obviously it is not going to stop at this, it being the equilibrium position. No, it is going to have a rotational motion, and in that case, yes, the torque will be produced. Given that the moment of inertia of the rod about A is ml square by 3, initial angular acceleration of the rod, net torque about point A will be equivalent to I alpha. Net torque about point A, that will be equivalent to I alpha. Right? Net torque about the point A, that will be equivalent to I alpha. Right? Okay. Now, which force is responsible for producing the torque? Suppose it is hinged at point A. So at point A, we are having two normal. One, this Ny and Nx. Right? So if you are calculating the torque about this point, then these two forces are not going to have any torque. Apart from this, we are having only one force, that is mg. So it means it is going to produce a torque. So it is mg, right, into L by 2, that is equivalent to I alpha. Moment of inertia there is given ml square by 3 into alpha. So what will be the angular acceleration? 3g by 2L. This is how the torque is calculated, right? 3g by 2L. The C is a perfect answer for this specific question. Okay, now let's move on to the most important concept, right? Let's move on to the concept of conservation of angular momentum. Students, this was about the talk. Now let's move on to the most important concept, right, of the conservation of angular momentum. What it states, right? See, first of all, I want to tell you all about the angular momentum, that you all are aware of that stuff. But right now we are going to see, right, what actually the conservation of the angular momentum is. Actually, there is a relation between the torque and the angular momentum, and that is torque, that is delta L by delta T. Change in angular momentum with respect to time, that defines the torque. Now, suppose in this case, suppose how the angular momentum is conserved. If net external torque on the system is 0, if net external torque on the system is 0, it means that, can I say del L by del T? For a very small change, it is written as dl by dt, right? For a very small change of a right angular momentum, it is written as dl by dt. So if a net external torque on the system is 0, right, can we consider as dl by dt, that is equivalent to 0, right? And if dl, any differentiation of any physical quantity, if it is 0, right, so it means that angular momentum is conserved. It means that, right, angular momentum, okay, is conserved, right? Okay, but this is conserved for the system, right? Right, this is conserved for the system, not for an individual particle. Right, for an individual particle, there is always change in momentum and angular impulses generated. Right, there is always change in momentum and angular impulses generated, but we are talking about the system. If net torque on the system is 0, net external torque on the system is 0, then and then only the angular momentum is conserved. Now let's see how we are going to use the stuff, right? Okay, see, a force F is acting on an point R, right? A force F is acting on an point R. The value of alpha at which angular momentum is conserved. Angular momentum is conserved, it means net external torque on the system is 0. It means dl by dt, that is equivalent to 0, or you can say R cross F, that is equivalent to 0. Three statements I'm keeping in front, right? Using any of the three statements, we are going to solve that stuff. R cross F is 0. What is the value of R? Obviously, the determinant is going to be 0. It is 2, minus 6, right, minus 12. What is the value of F? Right, it is alpha, 3, 6. Alpha, 3, 6. Right. Now in this case, right, okay, the torque will be 0. It means that, right, determinant I, J, K, right, and it is 2 minus 6 minus 12, alpha 3 and 6, this will be equivalent to 0. As usual, we have seen the, right, this 3 cross 3 determinant, and we are going to solve this, right, we are going to need this solution, right? So this torque will be 0 and it will be I, right? Let's convert this into the 2 cross 2, minus 6, 3, minus 12, 6, right, and minus J, 2 alpha, minus 12 and 6, right, and plus K, right, 2 alpha, minus 6 and 3, that will be equivalent to 0. Resolving this, you will get the value of the alpha as minus 1. In 2015, this kind of the question has been asked. This is the most important thing, right? See, sometimes in the JEE advanced question, right, if I'm talking about the JEE advanced level, right, then the question related to the angular momentum has been asked, right? But there is a maximum possibility, right, for an conservation of angular momentum to come into that. Right? Now let's see the next sum, what it states, right? A solid sphere is rotating freely about the symmetry axis in the free space. The radius of the sphere, see, solid sphere, radius of the sphere is increased. Radius is increased, right? Now mass is kept as same, right? Which of the following physical quantity would remain constant for the sphere? For angular momentum to get conserved, right, first of all, we need to check. What we need to check? Whether the net external torque on the system is 0 or not. Yes, here the net external torque on the system is completely 0. It means what? Angular momentum is conserved. dl by dt is equal to conserved for a system, and this angular momentum is going to be constant. This angular momentum is going to be constant. Right, so this is how the angular momentum is conserved. Let's move on to the next part. A thin circular ring of mass m and radius r is rotating about its axis with the constant angular velocity omega. Two objects of mass m are gently attached. This is a ring, right? It is rotating, right? Okay. So this is an initial situation. What will be the final situation, right? Two masses are attached to it. Okay, mass of the ring is capital M, right? Now suppose initially it was rotating with angular velocity omega. Now after these two masses are attached, the new angular velocity will be omega dash. This situation is given. The ring now, after attaching the two masses, the ring now is rotating with the new angular velocity, and that we need to calculate. The question is asked in May 2010 and in 1998. In this, first of all, I want to tell you all that the net external torque on the system is 0. It means angular momentum is conserved. Initial angular momentum that will be equivalent to final angular momentum. Initial angular momentum that is equivalent to I omega. I initial, omega initial. Final, this is I final, omega final. Initially only the not disk ring was rotating. So can I say its moment of inertia is capital M r square. It was rotating with constant angular velocity omega. Now masses are attached. So moment of inertia will be same mr square. Now these two are attached to n circumference, right? So obvious the radius of gyration will be r. So moment of inertia is small m r square plus, right, small m r square, right, into nu. They all will move with the constant angular velocity nu, that is omega dash. So here omega dash, it will be capital M of omega whole divided by capital M plus small m, right? This will be the perfect answer for this specific question. Right, this will be the perfect answer for this specific. And system, the net external torque is 0. Yes, the angular momentum is conserved. Suppose this thing is replaced by the 4 objects. A thin circular ring of mass m and radius r is rotating with the constant angular velocity omega. Now 4 objects are kept gently to an opposite ends. Initially disk was like this way, it was moving constantly. Its mass is m, its radius is r. It was constantly moving with the constant this angular velocity omega. This is an initial situation. Now what actually the final situation is? 4 objects of mass m are kept. Again, I want to tell you all, right, the momentum is conserved. Why? The net external torque on the system is 0. So it means momentum is conserved, right? Initial momentum that will be equivalent to final momentum. So what was the initial momentum? I omega mr square into omega. Final momentum, that is capital mr square plus 4 small mr square into omega dash. So what will be the new angular velocity? M omega whole divided by m plus 4 of m. Right? B is the perfect answer for this specific. Same. Now let's see what it states further. A solid cylinder of mass 3 kg is rolling on the horizontal surface with velocity. It collides. Okay, the situation is like this way. This is a solid cylinder. Right, it is rolling, velocity is given, it is 4 meter per second. Now here, right, spring is kept. Okay, it is not sliding, it is rolling. Rolling, it means that it is performing the rotational plus translational motion. The resultant of both, it is rolling. It is performing rotational plus translational. The resultant of both, it is the rolling. Right, the resultant of both, it is rolling. Now it is rolling and trying to compress this spring. So what is the maximum compression you can face into this? So this is a concept of the work energy theorem. Work done by all forces that will equivalent to change in kinetic energy of the object. But here we are not having any kind of these things, right? So here whatever the kinetic energy the cylinder holds while rolling, right, it is entirely transformed in compressing the spring. It means whatever the kinetic energy it holds, it is directly converting into the potential energy, and mechanical energy is conserved. So what this kinetic energy holds, right now it is rolling. So whenever any rigid body it is rolling, and it is having two types of the kinetic energies. The first one, it is a translational, and second one, it is a rotational. So here the translational kinetic energy plus rotational kinetic energy, that is equivalent to delta K. Sorry, that is equivalent to half kx square. Half kx square. Right. So here also, this is one of the applications, right, we have kept here. Okay. So there it is half mv square plus half I omega square, that is equivalent to half kx square. Replacing all of those stuff values are given, we get the x as 0.6 meter. X as 0.6 meter. It's a very simple thing. Right? Most important for the conservation of angular momentum, we are going to see here. This is rod, and it is hinged to this point. Bullet is coming. It is moving with velocity v meter per second. It gets embedded into it. Bullets get embedded, right? Okay, it gets, after collision, it gets embedded into it, right? Then what will be the new angular velocity of the system? If I'm talking about the entire system, so the net torque on the system is completely zero, net external torque on the system is zero, angular momentum is conserved, right? Now as angular momentum is conserved, can I say initial angular momentum, that is equivalent to final angular momentum? Initial angular momentum, that would be equivalent to what? Final angular momentum. What is the initial? See, angular momentum about the point A is conserved, right? So about point A, initial angular momentum is, right, mvr, final is I omega, right? Suppose this is of mass capital M, this is of mass small m, right? So initial is mvr, final is, now when it gets embedded into the, right, and they both starts rotating like this way, so this is the final situation, right? They both starts moving with the angular velocity omega, and the bullet is inside it. Now the system is of mass m plus capital M, right? So what will be the final moment of inertia with respect to point A? Small l is moving with L square, or you can say R square, right? This is also R plus, right? For rod, the moment of inertia will be ml square by 3. Right? Here L is equivalent to R only. Okay, and it is omega. So this is 4 by 3 m r square omega, and that is mv of r. Right? So this 1r is going to cancel, this m is going to cancel, 3v by 4r, this will be the new angular velocity of the rod after this get embedded into it. This is how the angular momentum is conserved, right? Okay, this is how the angular momentum is conserved, right? Now, apart from this conservation of angular momentum, right, obviously, right, one thing is remaining in this chapter, right, and that is the concept of rolling. Now, let's see what actually the rolling states. Okay, so students, let's move on to the most important concepts of the rolling, right? Okay, see, first of all, what does the rolling states? It itself states something that is rotation plus something that we are having translation. The resultant of this we are having as a rolling. It means at the same time the particle is rotating also and the particle is translating also. Let us take an example, right? Suppose this pen is rotating at this moment, right? So it is performing the rotational motion. Suppose the pen is sliding down, so it is performing the translatory motion. So something combination of both, that is rotational plus translational, is rolling, right? So let us take an example. Suppose this is the ground I'm going to take the example to understand this. Suppose this is a ground. The rolling is having the very less theories, right, to understand. Suppose this is a ground. Particle is rolling also with the angular velocity omega, right, and it is moving forward also with the linear velocity v. So after some time, the new position of the particle will be this, and it is again rotating with the omega. The new position of the particle will be this, and it is rotating with omega. New position of the particle is this. So it is rotating also, and it is getting translated also, right? So this kind of the motion, it is known as rolling. Basically, we are having the two types of the rollings, right? The first one, right, it is known as the forward slipping, and second one, right, it is known as backward slipping. Now, how we are going to classify this forward slipping, how we are going to classify this backward slipping, and how we are going to understand the concept of pure rolling, right? For this, right, we need to first of all understand, right, the velocity and the acceleration diagrams of the rolling. As I said, something that is rotated. Again, I am drawing this stuff. Okay, this is right, rotation plus translational, and in result we are getting this stuff, right? Velocity diagram of a particle that is rolling. See, the something that is, this is the translational motion of a particle. On a translational motion, right, the velocity of a particle on the right circumference is same, right? It is possessed by the velocity by the center of mass. Velocity at the each point when the particle is performing the translational motion, it is same. When it is performing the rotational motion, right, when it is performing the rotational motion, right, okay, then velocity is defined as like this way, r omega, right, r omega, r omega, r omega. So this is for the rotational motion. The resultant of this, we are having rolling. So it means, can I say at the top, V is also in this direction, R omega is also in this direction. So resultant is V plus R omega. Right? At this point, V is in this direction, right? R omega is in this direction. So resultant is in this direction. This is the resultant. Right? This is the resultant. At this point, V is in this direction, R omega is in this direction. So this is the resultant. At this point, V is in this direction and R omega is in this direction. So resultant is 0. This is the velocity diagram for the, right. This point is going to define whether the particle is going to perform pure rolling, the particle is going to perform, right, the forward slipping, or the particle is going to perform the backward slipping. This is the velocity diagram. Similarly, right, we are having the acceleration diagrams also for the rolling, right? Suppose this is the rotation, right, plus this is the translational, and this is equivalent to rolling, right? This is rolling, right, and this is rotational motion, and this is a translational motion. As the velocity at the each point, right, in the translational motion is same, so in this case the acceleration is also same at each point, right? The acceleration is also same at each point. For a rotational motion, we are having the two types of the acceleration. First, that is a tangential acceleration, that is r alpha, right? And for a particle that is moving, right? Okay, for that is performing the rotation, it is having the, right, omega square r, right? That is centripetal acting towards the center. Two types of accelerations are there, right, for a particle that is performing the rotation. One that is a tangential acceleration, second that is a centripetal. The resultant of this two is rolling. Resultant of this two is rolling. So at this point, A will be in this direction, R alpha will be in this direction, net acceleration is 0. Omega square r is in upward direction. At this point, A is in this direction, right? R omega is in this direction, omega square r is in this direction. Sorry, not r omega, it's r alpha, right? It's r alpha. At this point, A is in this direction, omega square r is in this direction, r alpha is in this direction. A plus r alpha, right? So this is what the acceleration diagram of the rolling is, right? Generally from rolling, right, the theoretical questions related to the forward slipping, backward slipping, right, and questions related to the diagram and the combination of this concepts with the work energy theorem is asked, right? Combination of this concept with the work energy theorem is asked. Now let's see this kind of the questions, right? Okay, but before that, let's analyze what actually the forward slipping and the backward slipping is. Now, if we have seen the velocity and the acceleration diagram of the rolling, you can see at this point, V minus R omega is 0. Even for the acceleration diagram, A minus R alpha is also 0. Right? V minus R omega is 0. A minus R alpha is 0. It means that the relative velocity of the particle at the bottom is 0 and the relative acceleration of the particle at the bottom is 0. It means this particle is not going to displaced. The relative motion between the particle and the bottommost contact surface is 0. Right? So as because of this, V is equivalent to R omega and A is equal to R alpha. These are the conditions of pure rolling. Right? Okay, these are the conditions of pure rolling. In pure rolling, the particle that is at the bottommost point does not perform any relative motion with respect to the contact surface. So in that case, A is equivalent to R alpha and V is equivalent to R omega at the bottommost point. Now here comes the forward slipping. Right. Here comes the forward slipping. In forward slipping, what happens? Right. The bottommost point, see, V is greater than R omega. It is moving right forward with the V and it is rolling with the R omega, right? So, forward slipping means what? The translational velocity of the particle is more as compared to the rotational one. Whenever, let us take an example, whenever you are applying the right side brake, not the disc brake of the front tire, right, then tire translates more, slides more as compared to the rotation. That's the best example of the forward slipping. So in that case, what will happen, right? Friction acts into the backward direction, right? So forward slipping, friction acts into the backward direction, right? And it will increase the rotational, it will increase the R omega, right? And after some time, pure rolling is attained. After some time, pure rolling is attained. What is a backward slipping? In backward slipping, V is less than R omega. A car tire stuck into the mud. Rotational part is more as compared to the translational one. So in that case, friction acting to the forward direction, right, that will decrease the omega. right, that will decrease the omega, and after some time, right, the pure rolling is attained. This is what the rolling is all about. And in rolling, basically there are two kind of the kinetic energies. First, that is a translational kinetic energy, and second one, that is a rolling this rotational kinetic. Now let's see one of two sums related to it, right? Because the applications of this with the work energy theorem are only asked into the examination. Okay, see, the speed of the homogeneous solid sphere after rolling down an inclined plane of vertical height h will be what? Solid sphere is rolling down, right? What is the speed at the bottommost point? It is rolling down. It means it is performing the rotational motion also, and it is performing the translational motion. So whatever amount of the potential energy he is possessing, right, it is right entirely converted into the kinetic energy. It means mgh. Now here it is having two types of kinetic energy. First, that is a translational kinetic energy. Second, that is a rotational kinetic energy. Right. So solving this stuff, we are getting m will so here mgh, that is equivalent to half mv square plus half, this will be 2 by 5 mr square omega square. Now it is rolling down, so can I replace here as v is equivalent to r omega? It is rolling down, na, right? So first of all, m will get cancelled, right? So gh, that is equal to v square by 2 plus, right, v square by 5. So v, that is equal to under root of 10 gh by 7. This is the velocity of the particle right at the bottommost point of an inclined plane. C is the perfect answer. So rolling, either from rolling related questions related to the work energy theorem was asked, in which two types of the conservations kinetic energy is there, or the questions from the velocity or acceleration diagrams are asked. Some Planck based questions are there. Right. Lots of questions are there, but it's okay. I will attach all of those stuff into the DPP. Right. For this, right, the important thing is all about the concept, what actually it states. A solid spherical ball rolls on the table. See, there is a spherical ball. It rolls on the table. Rolls, it means that it is performing the translational and rotational motion. Ratio of rotational kinetic energy. See, what is the rotational kinetic energy? Half I omega square. It is a solid sphere. So can I say half into 2 by 5 mr square omega square. So it is right mv square by 5. Consider this as equation number 1. Rotational kinetic energy to total. Total kinetic energy, that is equal to half I omega square plus half mv square, that is equal to 7 by 10 mv square. Right. So can I consider this as equation number 2? So ratio of right rotational right to total, that is equivalent to 2 by 7. Right. D is a perfect. That's the case of rolling. Apart from this, right, velocity of an particle rolling down an inclined plane, it is also asked, right? Okay, and acceleration of the particle, it's rolling down the inclined plane is also asked. So guys, this is a homework question from my side, right? Okay, so the most important part related to JEE and NEET, right, everything has been discussed in this chapter, right, with lots of examples, right? So guys, I think it's time to go, right? Okay, so guys, thanks a lot for whatever the love you that showered from your side, and I'm always used to see the comments. Okay guys, so it's time to go. So again, we will meet with the awesome teaser into the gravitation, and this is Indrajeet Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side. Bye everyone, stay at home, stay safe, stay healthy. Bye, take care amidst the pandemic. Bye everyone.